Welcome back. Tonight, we settle in with the gentle, unhurried story of how scientists learn to read the secret messages hidden in starlight, how a sliver of rainbow, passed through a prism in a quiet laboratory, could whisper the composition of suns burning trillions of miles away, and how, over more than a century of patient observation, the faint dark lines crossing those delicate spectra became a language, a cosmic alphabet revealing what the universe, in its vast silence, is actually made of. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights. Pull the blanket a little closer. And together, let us ease gently into tonight's story. In the final year of the 18th century, in a quiet house in the town of Slough, not far from Windsor Castle, the astronomer William Herschel was conducting a series of experiments that had nothing to do with the telescopes for which he was already famous. Herschel, who had discovered the planet Uranus some 19 years earlier and had spent much of his career mapping the heavens and building ever larger reflecting telescopes, found himself troubled by a practical problem. When he observed the sun through his telescopes, even with the darkened filters he used to protect his eyes, he noticed that different colored filters seemed to let through different amounts of heat. A red filter might keep his eyes safe but leave his face uncomfortably warm, while a green filter of seemingly equal darkness produced less of this heating effect. This simple observation, the kind of thing another person might have dismissed as a minor curiosity, led Herschel to wonder whether the different colors of light themselves carried different amounts of heat, and whether this heat could be measured and compared in some systematic way. To investigate this question, Herschel set up an arrangement that was elegant in its simplicity. He positioned a glass prism in a beam of sunlight entering through a window, allowing the prism to spread the white light into its familiar rainbow of colors, from red through orange and yellow and green and blue to violet. This was the same spectrum that Newton had described more than a century before, and any natural philosopher of the time would have been perfectly familiar with it. But where others had been content to observe the colors themselves, Herschel was interested in what he could not see. He obtained several sensitive mercury thermometers, the kind used for precise meteorological measurements, and he blackened the bulbs of these thermometers with ink or soot so that they would absorb as much radiant heat as possible rather than reflecting it away. He then placed these blackened thermometers, one at a time, in different regions of the colored spectrum, carefully recording the temperature readings as the thermometer came to equilibrium with the light falling upon it. The experiment required patience, as all good experiments do, and Herschel conducted it methodically over a period of weeks in early 1800. He was careful to use control thermometers placed just outside the colored spectrum, where no visible light fell, so that he could distinguish between the heating effect of the sunlight itself and the ordinary warmth of the room. These control thermometers showed him the baseline temperature, and any rise above this baseline in the thermometers placed within the spectrum could be attributed to the colored light. What Herschel found, as he moved his blackened thermometer from the violet end of the spectrum toward the red, was that the temperature readings increased steadily. The violet light produced a modest warming effect, the green somewhat more, and the red light produced the greatest warming of all the visible colors. This alone was an interesting result, confirming his earlier suspicion that red light carried more heat than blue or green. But then, on the 11th of February in the year 1800, Herschel made the observation that would expand humanity's understanding of light in a profound and lasting way. Having measured the temperatures throughout the visible spectrum, he moved his thermometer beyond the red end, into the region where no color could be seen at all. The spectrum appeared to end at red, fading into ordinary darkness, and there seemed no particular reason to expect anything of interest in that empty space. Yet when Herschel checked his thermometer, positioned just beyond the last visible traces of red light, he found that the temperature reading was higher than it had been within the red itself. There was heat present, considerable heat, in a region where no light was visible to the human eye. He moved the thermometer further still, and the temperature remained elevated. Some invisible influence was streaming from the prism along with the visible colors, and this influence carried warmth. Herschel, being a thorough experimentalist, repeated these measurements many times over the following weeks, varying the conditions, using different prisms and different thermometers, and always finding the same result. There existed beyond the red end of the spectrum a form of radiation that was imperceptible to human vision but that could be detected by its heating effect on matter. He called these invisible emanations calorific rays, from the Latin word for heat, and he speculated that they were a separate species of radiation, distinct from light itself. In his papers presented to the Royal Society later that year, Herschel carefully described his apparatus and his methods, his control measurements and his repeated trials, and he argued that the sun emitted not only the visible light that we perceive with our eyes but also these invisible calorific rays that we perceive only as warmth upon our skin. The Royal Society received Herschel's findings with considerable interest, as he was by then one of the most respected astronomers in Europe, and his work on telescopes and stellar astronomy had earned him the Copley Medal and the admiration of his peers. Nevertheless, the idea of invisible radiation was difficult for many to accept, and some natural philosophers questioned whether Herschel's calorific rays were truly a new form of radiation or merely ordinary heat conducted through the air or reflected from nearby surfaces. The skeptics suggested various alternative explanations, proposing that the heating effect beyond the red might be an artifact of the experimental arrangement rather than a genuine new discovery. Herschel addressed these objections methodically, demonstrating that his calorific rays could be reflected by mirrors and refracted by lenses, just as visible light could, and that they therefore possess the properties expected of a form of radiation. Over time, as other experimenters repeated and extended his work, the reality of what we now call infrared radiation became generally accepted, though the process of acceptance was gradual rather than immediate. Meanwhile, in the German city of Jena, a young natural philosopher named Johann Wilhelm Ritter was following Herschel's work with great interest and wondering whether the spectrum might extend in the other direction as well. If invisible radiation existed beyond the red, might there not also be invisible radiation beyond the violet? Ritter was particularly interested in chemical effects, in the way that light could cause certain substances to change color or decompose, and he knew that photographers and chemists had long observed that blue and violet light were especially active in producing chemical changes. Silver salts, for example, darkened when exposed to light, and this darkening happened more readily in blue light than in red. Ritter reasoned that if there were invisible rays beyond the violet, they might be even more chemically active than the violet light itself. In 1801, Ritter set up his own prismatic spectrum and placed strips of paper coated with silver chloride at various positions along it. Silver chloride, a white compound, turns dark when exposed to light because the silver is reduced to metallic form, and the degree of darkening indicates the amount of chemical activity produced by the light. Ritter observed, as others had before him, that the violet end of the spectrum produced more darkening than the red, confirming the known chemical activity of short wavelength light. But when he placed his silver chloride paper beyond the visible violet, in the region where no color could be seen, he found that the darkening was even more pronounced than it had been within the violet itself. There were invisible rays beyond the violet, and these rays were powerfully active in producing chemical change. Ritter called his discovery chemical rays or sometimes deoxidizing rays, emphasizing their ability to drive chemical reactions rather than their heating effect. Where Herschel's infrared rays were characterized by warmth, Ritter's ultraviolet rays were characterized by chemical activity, and this distinction between the calorific and the chemical would persist in scientific terminology for many years. Ritter was a romantic figure in the German scientific tradition, deeply influenced by the nat-philosophy movement that sought unity and polarity in natural phenomena, and he saw his discovery as revealing a fundamental symmetry in nature, with invisible radiation extending from both ends of the visible spectrum in a balanced and aesthetically pleasing way. His work was well received in German scientific circles, though it faced some of the same skepticism that had greeted Herschel's findings, with critics questioning whether the effects he observed might have other explanations. The discoveries of Herschel and Ritter arrived at a moment when the fundamental nature of light was itself a subject of intense debate. Isaac Newton had favored a corpuscular theory, imagining light as consisting of tiny particles emitted by luminous bodies, and this view had dominated optical thinking for much of the 18th century. But in the early years of the 19th century, the English polymath Thomas Young was reviving and extending the wave theory of light, proposing that light consisted of undulations in a subtle medium called the luminiferous ether. Young's famous double-slit experiment, performed around 1803, demonstrated interference patterns that were difficult to explain with particles but arose naturally from the superposition of waves. The wave theory would eventually triumph, particularly after the work of Augustin Fresnel in France, and it provided a natural framework for understanding the discoveries of Herschel and Ritter. If light was a wave phenomenon, then the different colors of the spectrum corresponded to different wavelengths of vibration, with red light having longer wavelengths and violet light having shorter ones. The invisible radiations discovered beyond the visible spectrum were simply extensions of this continuum, with infrared radiation having wavelengths longer than red and ultraviolet radiation having wavelengths shorter than violet. This new understanding transformed the very concept of what light was. Before Herschel and Ritter, light had been defined by human perception, by the sensation of brightness and color that we experience when electromagnetic radiation enters our eyes and stimulates our retinas. The visible spectrum, from red to violet, seemed to encompass all that light could be. But after 1800–1801, natural philosophers were forced to recognize that human vision samples only a narrow band of a much broader phenomenon. The radiation emitted by the sun and by other luminous bodies extends far beyond what our eyes can detect, and the visible colors are merely those wavelengths to which our particular biological senses happen to respond. Other creatures, with different eyes, might perceive different portions of the spectrum, and instruments could be built to detect radiations that no eye could ever see. This expansion of the concept of light laid the philosophical foundation for all that spectroscopy would become in the decades that followed. Once scientists understood that radiation existed beyond the visible, they began to wonder what other properties this radiation might have and what other information it might carry. The spectrum was no longer simply a display of colors, but a map of radiative energy extending in principle to indefinitely long and indefinitely short wavelengths. Instruments could be developed to explore these invisible regions, and each new region explored might reveal new phenomena and new insights into the nature of matter and energy. The work of Herschel and Ritter opened doors that their contemporaries could scarcely have imagined, leading eventually to the detection of radio waves and X-rays and gamma rays, and to the recognition that visible light is merely one small octave in the vast keyboard of electromagnetic radiation. In Slough and in Jena, working with prisms and thermometers and strips of chemically treated paper, two experimenters at the turn of the 19th century had glimpsed something profound. They had shown that the universe speaks in wavelengths we cannot see, that the sunlight falling on our faces contains messages written in colors beyond color, in radiations that pass through our visual experience unnoticed, but that can be coaxed into revealing themselves through careful measurement. The calorific rays and the chemical rays would eventually receive the more prosaic names of infrared and ultraviolet, but the wonder of their discovery persists, quietly, in every instrument that reaches beyond human vision to read the invisible signatures of distant stars and glowing nebulae and the faint warmth of cosmic backgrounds. These discoveries remind us, gently, that the world contains far more than our senses can directly apprehend, and that patient inquiry, conducted with simple apparatus and careful thought, can extend our awareness into realms we never knew existed. In the early years of the 19th century, in the quiet workshops and glass-making facilities of Bavaria, a young man who had known considerable hardship was beginning a patient investigation that would transform how humanity understood the nature of light itself, and in doing so, would lay the foundation for an entirely new way of reading the distant messages carried to us by starlight across the vast emptiness of space. Joseph von Fraunhofer came to this work not through the conventional pathways of university training or aristocratic patronage that characterized so much of European science at that time, but rather through a childhood marked by loss and labor, followed by a stroke of fortune so dramatic that it seemed almost to belong to the realm of folk tale rather than the sober pages of scientific history. Fraunhofer was born in 1787 in the town of Straubing, in what was then the electorate of Bavaria, the 11th child of a master glazier whose modest workshop provided the family with their livelihood. By the time Joseph reached the age of 11, both of his parents had died, leaving him orphaned and without the means to pursue any formal education beyond the most basic instruction he had received in his earliest years. The boy was apprenticed to a mirror maker and glasscutter in Munich, a man named Philipp Anton Weichselberger, who by most accounts was harsh in his treatment of the young apprentice, working him long hours and providing little in the way of training or care beyond what was strictly necessary. Joseph lived in his master's house under conditions that were difficult, and he was forbidden from pursuing any studies or reading that might distract from his labors at the grinding wheel and the cutting bench. It was in July of 1801, when Fraunhofer was 14 years old, that an event occurred which would alter the entire trajectory of his life in ways that no one could have anticipated. The old building in which Weichselberger kept his workshop and living quarters collapsed without warning, burying Joseph in the rubble along with others who had been inside at the time. The rescue efforts that followed attracted considerable attention in Munich, and among those who came to observe the work was Maximilian Joseph, the Elector of Bavaria himself, who watched as the young apprentice was pulled from the debris, injured but alive. Moved by the circumstances of the boy's survival and his evident lack of means, the Elector provided Fraunhofer with a gift of money, a sum of 18 ducats that was substantial enough to allow the young man to purchase his freedom from his apprenticeship and to acquire books and simple equipment for the self-directed study that his master had previously forbidden. This gift of fortune brought Fraunhofer to the attention of another benefactor who would prove even more influential in shaping his future, a man named Joseph von Utzschneider, who was a prominent figure in Bavarian commerce and industry, and who had established, along with a skilled optician named Georg von Reichenbach and a mathematician named Joseph Liebherr, an optical institute at the former Benedictine monastery of Benediktboyen in the Bavarian foothills. Utzschneider recognized in the young Fraunhofer an unusual combination of practical skill and intellectual curiosity, and he arranged for the young man to receive proper training and eventually to take on increasingly important responsibilities at the glassworks, where the manufacture of high-quality optical glass for telescopes, microscopes, and surveying instruments was the primary enterprise. At Benediktboyen, Fraunhofer found himself in an environment where his natural talents for precision work could flourish alongside a growing understanding of the theoretical principles underlying the behavior of light. The monastery had been secularized following the upheavals of the Napoleonic period, and its ancient buildings now housed furnaces and grinding workshops where craftsmen labored to produce lenses of greater clarity and accuracy than had previously been available. Fraunhofer rose through the ranks of this establishment with a quiet determination, becoming by 1809 a full partner in the Optical Institute and taking primary responsibility for the most demanding aspects of glass production and lens fabrication. It was in the course of his efforts to improve the quality of optical glass, and particularly to address the problem of chromatic aberration in telescope lenses, that Fraunhofer began his systematic investigation of the solar spectrum. He was not the first to notice that sunlight, when passed through a prism and spread into its constituent colors, displayed curious interruptions in the form of dark bands or lines crossing the otherwise continuous ribbon of the spectrum. William Hyde Wollaston, an English chemist and natural philosopher of considerable accomplishment, had observed such dark bands in 1802 while examining sunlight through a narrow slit and a prism, noting what he described as a series of dark lines that seemed to divide the spectrum into distinct colored regions. Wollaston, however, did not pursue this observation with any great persistence, and he interpreted the dark bands primarily as natural boundaries between the different colors rather than as phenomena requiring further investigation in their own right. Fraunhofer's approach to these dark lines was altogether more thorough and more patient, reflecting both his practical need to understand the precise behavior of light at different wavelengths and his temperamental inclination toward methodical, exhaustive measurement. Beginning around 1814, working in the quiet of the Benediktboyen glassworks, he constructed apparatus of unprecedented precision for the examination of the solar spectrum, combining carefully figured prisms with narrow slits and telescope optics that allowed him to magnify and examine the spectrum with a clarity that no previous observer had achieved. Where Wollaston had seen perhaps 7 dark bands, Fraunhofer began to discern hundreds of fine dark lines, some bold and easily visible, others faint and requiring careful attention to distinguish from a general background of colored light. Over the following years, Fraunhofer mapped these dark lines with extraordinary care, eventually cataloging more than 570 distinct features in the solar spectrum and assigning to the most prominent among them letter designations that are still in use today. The strongest and most easily observed lines he labeled with the letters A through K, proceeding from the red end of the spectrum toward the violet, and these letter designations became a standard vocabulary for spectroscopists in the decades that followed. The line he designated as D, which appeared in the yellow portion of the spectrum as a particularly bold and easily recognized feature, would later prove to be of special significance, and Fraunhofer measured its position with sufficient accuracy to place it at a wavelength that modern measurements confirm to be approximately 589 nanometers, a figure that speaks to the remarkable precision of his instruments and his observational technique. What made Fraunhofer's measurements possible was not merely his patience and his dedication, though both were considerable, but also his invention and refinement of tools that had not previously existed. Among the most important of these was the diffraction grating, a device consisting of many fine parallel lines ruled at equal intervals on a surface, which produces spectra through the interference of light waves rather than through the refraction of a prism. Fraunhofer created his earliest gratings by winding fine wire around two parallel screws at precisely controlled intervals, producing a series of equally spaced obstacles that would diffract incoming light into its component wavelengths. Later he developed techniques for ruling gratings directly onto glass surfaces, creating instruments of remarkable fineness and regularity that could spread light into spectra of great purity and resolution. The diffraction grating offered several advantages over the prism for the precise work of spectra measurement. Because the spacing of the grating lines could be measured directly, and because the mathematical relationship between line spacing, wavelength, and diffraction angle was well understood, the grating allowed Fraunhofer to assign actual numerical wavelength values to the dark lines he observed, rather than merely noting their positions relative to the visible colors. This capacity for absolute measurement was essential for transforming spectroscopy from a descriptive art into a quantitative science, and Fraunhofer's wavelength determinations for the principal solar lines remained standard references for many years after his death. Beyond his contributions to spectroscopy, Fraunhofer applied his deep understanding of light and his unmatched skill in glassmaking to the construction of telescope objectives of extraordinary quality. The most celebrated of these was the great refractor he built for the observatory at Dorpat, in what is now Estonia, which was completed in 1824 and represented the finest telescope of its kind anywhere in the world at that time. The Dorpat refractor had an objective lens of 9.5 inches in diameter, which may seem modest by the standards of later instruments but was remarkably large for its era, and its optical quality was so superb that Friedrich Georg Wilhelm Struve, the astronomer who used it, was able to accomplish observations of double stars and stellar positions that had previously been impossible. The instrument demonstrated that the theoretical understanding of light which Fraunhofer had developed through his spectroscopic work could be translated into practical improvements in the tools of astronomy, bringing clearer and more precise views of the heavens than had ever before been available. Throughout his years at Benedict Boyen and later at Munich, where the Optical Institute relocated in 1819, Fraunhofer worked with a quiet intensity that seemed to exclude consideration of his own health and well-being. The processes of glassmaking and lens grinding that occupied his days involved constant exposure to fine particles of glass dust and to the fumes of various chemicals used in polishing and treatment, and these conditions took a gradual but inexorable toll on his lungs. By his mid-30s, Fraunhofer's health had begun to decline noticeably, and he experienced increasing difficulty with breathing and persistent illness that weakened him even as his scientific reputation continued to grow. Joseph von Fraunhofer died in June of 1826, at the age of 39, having accomplished in his relatively brief life a body of work that would shape the development of physics and astronomy for generations to come. The cause of his death was consumption of the lungs, which almost certainly had been caused or substantially worsened by his years of exposure to the fine glass dust that was an unavoidable feature of his profession. He was buried in Munich, and the epitaph placed upon his memorial captured in 3 Latin words the essence of his contribution to human knowledge. The inscription read Approximavet Sidera, which may be translated as he brought the stars closer, a fitting tribute to a man whose mastery of light and of the instruments that shape it had indeed shortened the distance between humanity and the distant suns whose nature had for so long remained beyond reach. The dark lines that Fraunhofer mapped so carefully in the solar spectrum remained for some years a puzzle whose full significance was not yet understood. Fraunhofer himself observed that certain of the dark lines in sunlight corresponded exactly in position to bright lines that appeared when particular substances were heated to incandescence, and he noted especially a correspondence between his D line and the bright yellow light produced by burning sodium. But he did not live to see the full development of this insight, which would come in the following decades as other scientists built upon his foundational work and eventually unlocked the code that would allow the dark and bright lines of spectra to reveal the chemical composition of stars and nebulae and all the luminous objects of the cosmos. What Fraunhofer left behind was not merely a catalogue of lines or a set of instruments, though both were invaluable, but a demonstration of what could be accomplished through patient, precise observation combined with a deep understanding of the physical principles involved. His work showed that the light reaching us from the sun, and by extension from the stars, carried within it detailed information about the sources from which it came, information that was encoded in the patterns of brightness and darkness spread across the spectrum, and that could be read by anyone with the proper tools and the proper understanding. This was the beginning of a revolution in astronomy, a transformation that would eventually allow scientists to determine not merely where the stars were in the sky, but what they were made of, how hot they burned, how fast they moved, and countless other properties that had seemed forever beyond the reach of human inquiry. And so the story of spectroscopy begins in earnest with this quiet, diligent man from Bavaria, working by lamplight and furnace glow in the converted spaces of an old monastery, mapping with patient care the dark interruptions in the rainbow band of sunlight and inventing the instruments that would make such mapping possible with ever greater precision in the years to come. In the autumn of 1859, in a modest laboratory at the University of Heidelberg, two German scientists were about to accomplish something that philosophers had declared impossible, though they did not set out with such grand intentions, and indeed the story begins with something as simple and humble as a flame, the kind of steady blue flame that would come to bear one of their names and that still burns quietly in school laboratories around the world today. Robert Bunsen was a chemist, a man of careful habits and meticulous experimental technique, and he had spent years developing and refining a gas burner that produced a flame of remarkable purity, a flame that burned without the yellow flickering and sooty residue of ordinary combustion, a flame so clean and colorless that when chemical substances were introduced into it, the light emitted came entirely from those substances themselves and not from the burning fuel. This may seem a small detail, but it was precisely this small detail that made everything else possible. For previous attempts to study the light given off by heated elements had always been complicated by the interference of the flame itself, the contaminating glow of carbon particles and unburned gases obscuring the subtle colors that each element might contribute. Bunsen's burner, with its careful mixing of gas and air before ignition, burned with a flame that was almost invisible, almost perfectly transparent, a clear window through which the true colors of matter could finally be seen without distortion. Gustav Kirchhoff was a physicist, younger than Bunsen by 13 years, and where Bunsen was primarily interested in the practical identification of chemical substances, Kirchhoff brought to their collaboration a deeper theoretical curiosity about the nature of light itself, about the relationship between emission and absorption, about the fundamental laws that might govern how matter and radiation interact. The two men had become colleagues at Heidelberg, where Bunsen had arrived in 1852 and Kirchhoff in 1854, and their partnership represented one of those fortunate combinations of complementary talents that occasionally occur in the history of science, the experimentalist and the theorist working side by side, each contributing what the other lacked. Their method was straightforward in principle, though it required considerable skill and patience in practice. They would take small samples of various chemical elements and introduce them into the hot colorless flame of Bunsen's burner, where the heat would cause the atoms to emit light, and then they would observe this light through a spectroscope, an instrument consisting of prisms and lenses that spread the light into its component colors, just as Newton had done 2 centuries earlier, and just as Fraunhofer had done more recently with his precision gratings. What they saw, when they performed this procedure with different elements, was that each element produced its own unique pattern of bright-colored lines against the dark background of the spectrum, a kind of luminous fingerprint that belonged to that element alone and that could be used to identify it with absolute certainty even when present in the smallest quantities. Sodium, for instance, when heated in the flame, produced a pair of bright yellow lines very close together, so close that ordinary instruments could barely separate them, but so intense that even traces of sodium contamination would cause them to appear. These yellow lines fell at precisely the same position in the spectrum as the pair of dark lines that Fraunhofer had labeled D in his map of the solar spectrum, those same lines that had puzzled observers for decades, and this coincidence was striking enough that it could not easily be dismissed as mere chance. Kirchhoff and Bunsen found that every element they tested produced its own characteristic set of lines, and that these lines always appeared at exactly the same wavelengths regardless of how the element was heated or in what quantities it was present, suggesting that these spectral signatures were a fundamental property of the atoms themselves, as unchanging and reliable as any physical constant. It was Kirchhoff who formulated the theoretical framework that made sense of these observations, and in 1859 he presented what would become known as the three laws of spectroscopy, though he did not number them himself in quite that fashion, and they have been stated in various ways by subsequent generations of teachers and textbook writers. The first of these principles states that a hot solid object, or a hot dense gas, produces a continuous spectrum of light, a smooth rainbow containing all colors without any gaps or interruptions, the kind of spectrum that sunlight would produce if the sun were merely a glowing sphere of hot matter without any cooler gases surrounding it. The second principle states that a hot thin gas, such as the vapors of a chemical element heated in a flame, produces an emission spectrum consisting of bright lines at specific wavelengths characteristic of that element, with darkness between the lines where no light is emitted. The third principle, and this was perhaps the most subtle and the most consequential, states that if light having a continuous spectrum passes through a cooler thin gas, the gas will absorb light at precisely those same wavelengths where it would emit light if heated, producing dark absorption lines against the bright continuous background. This third law was the key that unlocked the mystery of the Fraunhofer lines, for it suggested that the dark lines in the solar spectrum were not defects or gaps in the sun's luminous output, but rather the signatures of cooler gases through which the sunlight had passed, gases that had absorbed specific wavelengths and left their marks as shadows across the spectrum. The matching of the solar D line with the emission lines of sodium was therefore not merely a curious coincidence but evidence of a profound physical truth, namely that sodium atoms existed in the atmosphere of the sun, absorbing the same wavelengths of light that they would emit if heated, behaving according to the same natural laws in that distant celestial furnace as they did in the modest flame of a Heidelberg laboratory. But Kirchhoff was a careful scientist, and he wanted more than a suggestive match of line positions to support this extraordinary claim. In October of 1859, he performed an experiment that would become one of the most celebrated demonstrations in the history of spectroscopy, an experiment that revealed the precise reciprocity between emission and absorption with elegant clarity. He arranged his apparatus so that sunlight passed through a sodium flame before entering his spectroscope, reasoning that if the sodium atoms in the flame and the sodium atoms in the sun were truly behaving according to the same physical laws, their interaction should produce a predictable result. What he observed was remarkable and at first somewhat counterintuitive, for instead of the sodium flame adding its bright yellow light to the solar spectrum and filling in the dark D lines, the D lines actually became darker, more pronounced, more deeply shadowed than they had been in the original sunlight alone. This apparent paradox resolved itself upon careful consideration, for the flame was indeed emitting light at the D wavelengths, but it was also absorbing light at those same wavelengths from the more intense beam of sunlight passing through it, and because the sunlight was so much brighter than the flame's emission, the net effect was increased absorption rather than compensation. The experiment demonstrated beyond reasonable doubt that emission and absorption were mirror processes, two aspects of the same fundamental interaction between matter and light, and that the presence of sodium in the solar atmosphere could be inferred with as much confidence as if someone had collected a sample of the sun and brought it back to the laboratory for analysis. The implications of this discovery were profound and perhaps difficult to fully appreciate in our current age, when the chemical composition of distant stars and galaxies is routinely determined by spectroscopic methods. For centuries, the heavens had seemed utterly remote from the earthly realm of chemistry, and there was a widespread belief, even among educated and scientifically minded people, that the composition of the stars would forever remain beyond the reach of human knowledge. This belief had been expressed most famously by the French philosopher Auguste Comte, who in 1835 had written in his Cause de Philosophie Positive that while we might study the shapes and motions of celestial bodies, their distances, and their sizes, we could never by any means know their chemical composition or their mineralogical structure, that such knowledge was necessarily and permanently barred from human attainment by the very nature of the case. Comte had chosen stellar composition as his example of intrinsically unknowable information, the kind of question that positive philosophy should not waste its time pursuing, and for a quarter of a century his assessment had seemed reasonable enough, for no one could see how samples of the sun or stars might ever be obtained for laboratory analysis. Yet here were Kirchhoff and Bunsen, barely 2 decades after Comte's confident pronouncement, demonstrating that the very light from the sun carried with it detailed information about the elements present in its atmosphere, that no sample need be physically collected because the spectrum itself was a kind of chemical message sent across 93 million miles of space, perfectly legible to anyone with the proper instruments and the theoretical understanding to read it. The Heidelberg laboratory became, in the months following this initial discovery, a site of intensive investigation, as Kirchhoff and Bunsen systematically compared the emission spectra of various elements with the absorption lines in the solar spectrum, identifying the presence of iron, magnesium, calcium, chromium, and other familiar substances in the atmosphere of the sun. Each match of an emission line with an absorption line was another piece of evidence, another confirmation that the distant star that warmed and illuminated the Earth was made of the same stuff as the Earth itself, that the universe was chemically unified in ways that no one had previously had the means to demonstrate. But the spectroscopic method proved useful not only for identifying known elements but also for discovering new ones, elements that had never been isolated or recognized before but that revealed themselves through their distinctive spectral fingerprints. In 1860, while analyzing the spectrum of mineral water from Durkheim, Bunsen and Kirchhoff observed a pair of blue lines that did not match any known element in their catalogue of spectra, and they concluded that these lines must belong to a previously unknown substance, which they named cesium from the Latin word for sky blue, describing the color of those characteristic spectral lines. The following year, in 1861, they detected another unfamiliar set of lines, this time in the deep red portion of the spectrum, while analyzing the residue of certain mineral waters, and they named this second new element rubidium, from the Latin word for deep red, again taking their name from the color of the spectral signature by which the element had first been recognized. These discoveries were remarkable not only for adding 2 new elements to the periodic table but for demonstrating an entirely new method of chemical discovery, a method that did not require the physical isolation of a pure sample but could identify the presence of an element through its light alone, even when that element was present in quantities too small to be detected by any other means. Spectroscopy had become a tool of extraordinary sensitivity and specificity, capable of revealing atomic identities across any distance that light could travel, whether the length of a laboratory bench or the vastness of interstellar space. The work of Kirchhoff and Bunsen thus represents a turning point in humanity's understanding of the cosmos, a moment when the barrier between terrestrial and celestial chemistry was dissolved forever, when the stars ceased to be mysterious lamps of unknown substance and became instead familiar congregations of the same atoms that could be found in any earthly rock or sample of seawater. The method they developed would be refined and extended by subsequent generations of scientists, applied to ever more distant objects and ever more subtle questions, but the fundamental insight was theirs, formulated in that quiet laboratory in Heidelberg during those months of patient observation and careful reasoning, when a chemist with a clean flame and a physicist with a gift for theory together read the composition of the sun in the colored shadows of its light. The sun, that familiar companion to all our days, has served as a kind of laboratory suspended in the sky, offering itself to the patient inquiries of those who wish to understand what stars are made of, and how such knowledge might be coaxed from the light that travels so far to reach us. In the middle decades of the 19th century, as the science of spectroscopy matured and the techniques for analyzing light became more refined, astronomers began to turn their instruments toward our nearest star with a new sense of purpose, knowing that the sun's proximity meant its light arrived with sufficient intensity to be spread and studied in ways that the fainter stars did not yet permit. What they found in that sunlight would reshape the very notion of what astronomy could tell us, revealing not merely the positions and motions of celestial bodies, but the very substances of which they are composed, and in one remarkable instance, the existence of an element that had never been seen on Earth at all. To understand how such a discovery came about, we must first appreciate the particular opportunities that solar eclipses afforded to those who studied the sun. Under ordinary circumstances, the overwhelming brightness of the solar disk makes it quite difficult to examine the fainter regions that lie just above its visible surface, that thin shell of glowing gas known as the chromosphere, which takes its name from the Greek word for color owing to its reddish appearance during those brief moments when the moon blocks the main body of the sun from view. During a total eclipse, with the brilliant photosphere hidden behind the lunar disk, this chromosphere becomes visible to the eye and to the spectroscope alike, offering a chance to study light that would otherwise be lost in the glare. It was precisely such an opportunity that drew the French astronomer Pierre-Jules César Janssen to travel a great distance in the summer of 1868, making his way to the town of Guntur in southeastern India, where the path of totality would pass on the 18th of August and where, if the weather proved cooperative, he might train his spectroscope upon the briefly revealed solar atmosphere. The journey itself was considerable, requiring Janssen to transport his instruments across oceans and continents to reach a position where the eclipse would be total, and such expeditions were becoming increasingly common in this era, as astronomers recognized that eclipses offered windows of scientific opportunity that could not be replicated by any other means. When the day arrived and the moon's shadow swept across the Indian landscape, Janssen was ready, his spectroscope directed at the chromosphere as it emerged into view around the limb of the darkened sun. What he observed in those precious moments of totality was a series of bright emission lines, the glowing signatures of the hot gases that make up that outermost layer of the solar atmosphere, and among these lines was one that immediately attracted his attention, a bright yellow line that did not correspond to any element known to chemistry at that time. This line lay at a wavelength of approximately 587.49 nanometers, quite close to the familiar yellow lines of sodium but distinctly separate from them, occupying its own position in the spectrum and refusing to be identified with any substance that had been isolated and studied in terrestrial laboratories. Janssen was sufficiently intrigued by this observation that he returned to examine the chromosphere on the following days, and he made a discovery that would prove important for future solar research, finding that the chromospheric emission lines were bright enough to be observed even without an eclipse, provided one used a spectroscope with sufficient dispersion to spread the solar light and isolate the chromospheric emissions from the continuous spectrum of the photosphere beneath. This meant that the study of the chromosphere need not be confined to the rare and fleeting moments of totality, but could in principle be conducted on any clear day, a realization that opened new avenues for solar spectroscopy and allowed the mysterious yellow line to be examined at leisure. Meanwhile, quite independently, and without knowledge of Janssen's observations in India, the English astronomer Joseph Norman Lockyer was conducting his own spectroscopic studies of the sun from his home in London. Lockyer had been developing techniques for observing solar prominences and the chromosphere without the need for an eclipse, using a spectroscope with a narrow slit and sufficient dispersive power to separate the bright emission lines of the chromosphere from the background glare. In October of 1868, some 2 months after the eclipse that Janssen had observed, Lockyer succeeded in examining the solar chromosphere from his London observatory and noted the same anomalous yellow line that Janssen had recorded, recognizing that it did not match any known terrestrial element. The two men had arrived at the same conclusion by different paths, and when their reports reached the French Academy of Sciences, the letters arrived on the same day, a coincidence that was commemorated by the striking of a medal bearing both their likenesses in recognition of their simultaneous and independent discovery. Lockyer was particularly struck by the implications of this unknown line, and he proposed that it represented an element that existed in the sun but had not yet been found on Earth. He gave this hypothetical element the name helium, drawing upon the Greek word helios, meaning sun, in acknowledgement of the celestial origin of its discovery. It was a bold suggestion, for at that time the notion that an element might exist in the heavens before being found on our own planet seemed to some a rather fanciful idea, and there were those who suspected that the mysterious line might eventually be explained as belonging to some known element under unusual conditions of temperature or pressure. Yet Lockyer maintained his conviction, and the name helium passed into use among those who discussed this curious feature of the solar spectrum, even as the element itself remained stubbornly absent from earthly laboratories. The confirmation of helium as a genuine element would require patience, for 26 years would pass between its spectroscopic identification in the sun and its isolation on Earth. During this long interval, the yellow line at 587 nanometers remained a kind of spectrum mystery, acknowledged but unexplained, a reminder that the Sun might harbor substances unknown to terrestrial chemistry. It was not until 1895 that the Scottish chemist William Ramsay, working at University College London, succeeded in isolating helium from a terrestrial source. Ramsay had been investigating the gases released when certain uranium-bearing minerals were treated with acid, and when he examined a sample of clavate, a variety of uraninite ore, he found that it released a gas that did not behave like any known substance. When this gas was subjected to spectroscopic analysis, it displayed the characteristic yellow line that Lockyer and Janssen had observed in the solar chromosphere nearly 3 decades earlier, confirming at last that helium was indeed a real element and that it had been present on Earth all along, locked within the crystal structures of certain minerals and waiting to be released by the patient inquiries of chemistry. The discovery that helium existed on Earth as well as in the Sun was a moment of considerable satisfaction for those who had championed the spectroscopic method, for it demonstrated that the analysis of light could reveal truths about the composition of distant objects that would later be confirmed by direct laboratory investigation. Helium would prove to be no mere curiosity, but the second most abundant element in the universe, present in stars and nebulae throughout the cosmos, and its terrestrial rarity a reflection of its lightness and its tendency to escape the gravitational hold of our small planet rather than any fundamental scarcity in the broader scheme of things. We should step back now to consider the broader context in which these discoveries took place, for the analysis of the solar spectrum had been proceeding along several fronts during the years leading up to Janssen and Lockyer's observations. Among the most important contributors to this work was the Swedish physicist Anders Jonas Ångström, who devoted himself to the painstaking task of mapping the solar spectrum with unprecedented precision. In 1862, Ångström published a detailed atlas of the solar spectrum, presenting the wavelengths of numerous Fraunhofer lines with a degree of accuracy that far surpassed previous measurements. His work provided a standard reference that other spectroscopists could use to compare their own observations, and his careful attention to measurement established benchmarks that would guide the field for decades to come. So influential was Ångström's contribution that the unit of wavelength he employed, equal to 1/10 billionth of a meter, came to bear his name, and the Ångström unit remains in use today as a convenient measure for expressing the wavelengths of visible light and the dimensions of atoms and molecules. The study of the Sun during eclipses continued to yield important insights in the years following the helium discovery, and in 1870, the American astronomer Charles Augustus Young made an observation that shed new light on the structure of the solar atmosphere. Young had traveled to Jerez de la Frontera in southern Spain to observe the total eclipse of that year, and as he watched the moment when the moon's disk covered the last sliver of the photosphere, he noticed something remarkable in his spectroscope. In the instant before totality, the dark Fraunhofer lines of the solar spectrum briefly reversed, flashing into bright emission lines for just a few seconds before the chromosphere became visible in its usual form. This phenomenon, which Young called the flash spectrum, revealed the presence of a thin layer at the very base of the chromosphere, a region that he termed the reversing layer, where the gases responsible for the absorption lines in normal sunlight became visible as emitters in their own right. The reversing layer represented the transition zone where the relatively cool gases that absorb light from the hotter photosphere below give way to the hotter, more tenuous gases of the chromosphere above, and its observation helped astronomers to build a more complete picture of the Sun's layered atmosphere. While the Sun offered the brightest and most accessible target for spectroscopic study, astronomers were also beginning to extend their techniques to the fainter light of other stars, seeking to determine whether the same elements that composed our Sun might be found throughout the stellar realm. This work was challenging, for stellar light arrives at Earth greatly diminished by distance, and spreading it into a spectrum reduces its intensity further still, requiring long exposures and sensitive detection methods. The American physician and amateur astronomer Henry Draper made a significant advance in this direction in 1872, when he became the first person to successfully photograph the spectrum of a star, choosing for his subject the bright star Vega in the constellation Lyra. Draper's photograph captured the dark absorption lines crossing the stellar spectrum, demonstrating that the same techniques of spectral analysis that had proven so fruitful for the Sun could be applied to stars as well, and that the chemical composition of distant suns might be read from the light just as Kirchhoff and Bunsen had read the composition of flames in the laboratory. The photograph itself was a technical achievement of some note, requiring Draper to construct specialized equipment and to develop techniques for guiding his telescope with sufficient precision to keep the stellar image steady on the photographic plate during the long exposure required. The resulting image, showing the familiar pattern of absorption lines against the continuous spectrum of starlight, opened a new chapter in astronomical observation, for photographs could capture details that the eye might miss, could be examined at leisure after the observation was complete, and could be shared among investigators who might never have the opportunity to observe the original star themselves. Photography would become an indispensable tool in the spectroscopic study of stars, allowing catalogues of stellar spectra to be compiled and compared in ways that visual observation alone could not easily permit. These various strands of investigation, the eclipse observations of Janssen and Young, the careful measurements of Angstrom, the spectral photography of Draper, the laboratory work of Ramsay, all contributed to a growing understanding of the Sun as a physical object, a sphere of hot gas whose composition could be determined and whose structure could be mapped through the patient analysis of light. The Sun had become, in a sense, a laboratory accessible from Earth, a place where the behavior of matter under extreme conditions could be studied through the messages encoded in its spectrum. The discovery of helium stood as a testament to the power of this approach, demonstrating that spectroscopy could reveal the existence of elements before they were ever held in human hands, and that the light of the Sun carried information about the fundamental constituents of matter that no other method of inquiry could provide. As the 19th century drew toward its close, the solar laboratory had established itself as one of the most fruitful domains of astronomical research, offering insights into the nature of stars and the substances of which they are made, insights that would continue to deepen as new techniques and new instruments were brought to bear upon the ancient and unvarying light of our nearest star. In the quiet years following the work of Kirchhoff and Bunsen, astronomers found themselves in possession of a remarkable tool, one that could reveal the chemical nature of distant suns, and yet the question remained of how best to make sense of the tremendous variety of stellar spectra that their instruments were now capable of recording. For while it was one thing to observe that stars displayed different patterns of dark absorption lines against their continuous rainbow backgrounds, it was quite another matter to organize these differences into a coherent system, to find order amid the apparent chaos of thousands upon thousands of individual stellar signatures, each one slightly different from the next in ways that seemed, at first glance, almost arbitrary in their variation. The first truly systematic attempt to impose order upon this celestial diversity came not from the great observatories of Germany or England, but from the modest rooftop observatory of the Roman College in Vatican City, where a Jesuit priest named Angelo Secchi had been quietly pursuing his astronomical work since the 1850s. Father Secchi was a gentle and methodical man, trained in physics and mathematics, who had spent time in both England and America before returning to Rome to take up his position as director of the observatory, and he brought to his work a patience and a dedication to careful observation that would prove essential to the task he was about to undertake. Beginning in 1863 and continuing through to 1868, Secchi embarked upon a program of visual spectroscopy that was remarkable both for its ambition and for its simplicity. Using a relatively modest refracting telescope fitted with a spectroscope of his own design, he observed the spectra of more than 4,000 stars with his own eyes, recording their characteristics by hand and gradually sorting them into groups based upon their shared features. It was painstaking work, requiring clear nights and steady hands and eyes that could discern subtle differences in the patterns of dark lines crossing each stellar spectrum, and Secchi pursued it with the quiet persistence that characterized all of his scientific endeavors. What emerged from these thousands of individual observations was the first comprehensive classification scheme for stellar spectra, a system that divided the stars into 4 basic types according to the overall appearance of their spectral patterns. The first type, which Secchi designated Type 1, comprised stars like Sirius and Vega, whose spectra were dominated by strong hydrogen lines and appeared bluish-white to the eye, stars that we would now recognize as being among the hottest in the heavens. Type 2 included yellowish stars like our own Sun and the bright star Capella, whose spectra showed numerous fine metallic lines in addition to somewhat weaker hydrogen features, indicating a slightly cooler temperature and a more complex atmospheric chemistry. Type 3 encompassed the orange and reddish stars such as Betelgeuse and Antares, whose spectra displayed broad dark bands that Secchi correctly attributed to the presence of molecular compounds, substances that could only form in the relatively cool outer atmospheres of these aging giant stars. And Type 4, the smallest category, consisted of deep red stars with carbon-rich spectra, objects that we now understand to be in the late stages of stellar evolution. Secchi's classification was beautifully simple and immediately useful, providing astronomers with a common language for describing stellar spectra and revealing, for the first time, that the apparently random differences among stars could be reduced to a manageable number of basic categories. Yet even as Secchi was completing his visual survey in Rome, the technology of astronomical observation was undergoing a transformation that would render his methods, however elegant, fundamentally obsolete, for the development of dry photographic plates in the 1870s meant that spectra could now be recorded permanently on glass, examined at leisure, measured with precision, and preserved for future generations of astronomers to study and compare. It was at the Harvard College Observatory in Cambridge, Massachusetts, that the full potential of photographic spectroscopy would be realized, under the direction of Edward Charles Pickering, who assumed the position of observatory director in 1877 and immediately set about transforming the institution into a center for large-scale astronomical survey work. Pickering was an unusual figure in American astronomy, a man who combined genuine scientific insight with exceptional organizational abilities and a talent for securing the financial support necessary to pursue ambitious research programs. He understood, perhaps more clearly than any of his contemporaries, that the future of astronomy lay not in the study of individual objects, however interesting, but in the systematic observation and cataloging of vast numbers of stars, building up statistical databases from which general laws and patterns might eventually emerge. In 1886, Pickering initiated a photographic survey of stellar spectra that would continue for decades, employing a technique known as objective prism spectroscopy, in which a large prism was placed in front of the telescope objective, causing each star in the field of view to produce its own small spectrum on the photographic plate. This method was wonderfully efficient, allowing hundreds of stellar spectra to be recorded simultaneously on a single exposure, and the Harvard collection of spectroscopic plates would eventually grow to encompass hundreds of thousands of individual stellar spectra, an archive of stellar light that remains valuable to astronomers even today. Yet the accumulation of photographic plates was only the beginning of the work, for each spectrum had to be examined, classified, and recorded in catalogues before it could contribute to astronomical knowledge, and this labor of examination and classification proved to be far more demanding than Pickering had initially anticipated. The story of how Pickering came to assemble his remarkable team of women assistants, the group that would later become known as the Harvard Computers, has been told in various ways over the years, but the essential facts remain consistent. In 1881, frustrated by the careless work of his male assistant, Pickering declared that his Scottish maid could do a better job, and then proceeded to hire her to prove his point. That maid was Williamina Patton Stevens Fleming, a young woman who had emigrated from Dundee to Boston with her husband only to find herself abandoned and pregnant, taking domestic work in the Pickering household to support herself and her coming child. Fleming had received a good education in Scotland, including training in mathematics and bookkeeping, and she quickly demonstrated an aptitude for the precise and methodical work of examining photographic plates and recording spectral characteristics. Pickering recognized her abilities and gradually expanded her responsibilities, eventually placing her in charge of the spectral classification program and authorizing her to develop a systematic scheme for organizing the growing collection of stellar spectra. Fleming's classification system, which she developed over several years of careful work, built upon Secchi's original 4 types but subdivided them much more finely, assigning letters of the alphabet to different spectral categories based primarily on the strength of the hydrogen absorption lines. Her scheme ran from A through Q, with A-type stars showing the strongest hydrogen lines and subsequent letters indicating progressively weaker hydrogen features, and this lettered system would form the foundation upon which all subsequent stellar classification would be built, even though the letters themselves would eventually be rearranged into a different and more physically meaningful sequence. Fleming worked for modest wages, as did all of the women who would join her at the Harvard Observatory over the following decades, earning between 25 and 50 cents per hour for labor that required intelligence, education, careful attention to detail, and long hours of eye-straining work examining photographic plates through magnifying glasses. These wages were comparable to those paid to skilled factory workers and substantially lower than what male astronomers earned for similar work. Yet the positions offered intellectual stimulation and a degree of professional recognition that were largely unavailable to women in other fields, and Fleming and her colleagues pursued their work with dedication and enthusiasm despite the financial limitations. Among the women who joined Fleming at Harvard was Annie Jump Cannon, who arrived in 1896 having already earned a degree in physics from Wellesley College and possessing a passion for astronomy that had led her to spend a year studying at Radcliffe. Cannon was partially deaf, the result of a childhood illness, and perhaps her relative isolation from the social world around her contributed to her extraordinary powers of concentration, for she would eventually become the most prolific classifier of stellar spectra in the history of astronomy, examining and categorizing hundreds of thousands of stars over her long career at Harvard. Beginning in 1901, Cannon undertook a fundamental revision of the spectral classification system, rearranging Fleming's alphabetical categories into a new sequence that reflected the actual physical progression of stellar temperatures from hottest to coolest. In Cannon's revised scheme, the sequence ran O, B, A, F, G, K, M, with O-type stars being the hottest and bluest and M-type stars being the coolest and reddest, and each major class was further subdivided into 10 numerical subclasses from 0 to 9, allowing for precise characterization of subtle spectral differences. The letters themselves were remnants of Fleming's original alphabetical system, preserved despite their seemingly arbitrary order because they had already become familiar to astronomers, and changing them entirely would have caused unnecessary confusion. Cannon's rearranged sequence would acquire a mnemonic aid, a phrase to help students remember the seemingly random progression of letters, and the version that became most widely used was "Oh, be a fine girl, kiss me," a sentence attributed to the astronomer Henry Norris Russell, who was then at Princeton and who would later make his own fundamental contributions to the understanding of stellar classification. The phrase has a somewhat dated quality to modern ears, but it served its purpose well, and generations of astronomy students have used it to fix the spectral sequence in their memories, the gentle absurdity of the words somehow making them easier to recall than the bare letters alone. Working with remarkable speed and accuracy, Cannon classified more than 350,000 stars for the Henry Draper Catalogue, a massive compilation of stellar spectra that was published in 9 volumes between 1918 and 1924 and named in honor of the pioneering astrophotographer whose widow had funded the spectroscopic survey. At the peak of her productivity, Cannon could classify several hundred stars per hour, glancing at each small spectrum on the photographic plate and immediately recognizing its type from subtle features that her long experience had made second nature. And the catalogue she produced remains an essential reference work in stellar astronomy more than a century after its completion. Yet the Harvard classification system, for all its practical utility, was not without its limitations, and one of the earliest to recognize this was Antonia Mori, another of Pickering's women assistants, who was the niece of the observatory's benefactor Henry Draper and who possessed both the education and the temperament to question established methods. In 1897, Mora published her own classification scheme, which included not only the basic spectral types but also a notation for the appearance of the spectral lines themselves, distinguishing between stars with broad fuzzy lines and stars with sharp well-defined lines by adding a prefix C to indicate the latter characteristic. Maury's observation was more significant than it might at first appear, for the sharpness of spectral lines depends not only on the temperature of a star but also on its luminosity, with giant stars of low density producing sharper lines than dwarf stars of the same temperature but higher density. Her C-type stars were, in effect, the first recognition of what would later be called luminosity classes, a second dimension of stellar classification that would eventually prove essential to understanding the true nature of the stars and their evolutionary histories. Pickering initially dismissed Maury's refinements as unnecessarily complicated, preferring Cannon's simpler system for the practical work of the Henry Draper Catalogue, but later astronomers would vindicate Maury's insight, and her sharp-line C-type stars would become recognized as supergiants, the largest and most luminous stars in the universe. And so, through the patient labor of these remarkable women and their colleagues, the chaos of stellar spectra was gradually reduced to order, the rainbow light of distant suns sorted and classified and recorded in catalogues that would enable the next generation of astronomers to begin the work of understanding what these spectral differences truly meant. The classification itself was descriptive rather than explanatory, a taxonomy of stellar light rather than a theory of stellar physics, and yet it provided the essential foundation upon which all subsequent work would build, the organized data from which physical understanding would eventually emerge. In the quiet rooms of the Harvard Observatory, under electric lights and with magnifying glasses in hand, the Harvard computers had created a map of the stellar heavens, a guide to the diversity of suns that would serve astronomy for generations to come. In the year 1842, in the city of Prague, a mathematician named Christian Doppler presented a paper to the Royal Bohemian Society of Sciences, a paper that would eventually change how we understand the motion of everything in the universe, though its implications would take many years to fully unfold. Doppler was interested in a phenomenon that anyone might notice in everyday life, if they pause to consider it carefully, which is that the pitch of a sound seems to change depending on whether the source of that sound is moving toward you or away from you. A church bell ringing from an approaching carriage sounds slightly higher in pitch than the same bell would sound if the carriage were stationary, and as the carriage passes and moves away, the pitch drops slightly lower. Doppler worked out the mathematics of this effect, showing that the observed frequency of a wave depends not only on the frequency at which the source emits it, but also on the relative motion between the source and the observer, and he published his theoretical analysis in a paper with the rather lengthy title On the Colored Light of the Binary Stars and Some Other Stars of the Heavens. Doppler himself was primarily thinking about sound waves when he developed his theory, and he made the curious suggestion that the different colors of stars might be explained by their motions toward or away from Earth, with approaching stars appearing bluer and receding stars appearing redder. This particular application was not quite correct, as it turned out, because stars are not single-frequency sources of light and their intrinsic colors depend on their temperatures, but the underlying principle that Doppler had identified was absolutely sound, and would prove to be one of the most powerful tools ever developed for studying the cosmos. The mathematics showed that when a source of waves moves toward an observer, the waves are compressed slightly, making their wavelength shorter and their frequency higher, and when the source moves away, the waves are stretched, making their wavelength longer and their frequency lower. The faster the motion, the greater the shift in wavelength, and this relationship could be expressed in a simple equation that connected the change in wavelength to the velocity of the source. A few years later, in 1848, a French physicist named Amand Hippolyte Louis Fizeau independently arrived at similar conclusions and extended the analysis more explicitly to light waves, recognizing that the effect would manifest itself not as a change in the overall color of a star, but as a shift in the positions of the dark spectral lines that Fraunhofer had mapped so carefully decades before. Fizeau understood that these sharp, well-defined lines served as precise markers of specific wavelengths, and if a star were moving toward or away from Earth, all of these lines would shift slightly from their normal positions, toward the blue end of the spectrum if the star were approaching, and toward the red end if the star were receding. The beauty of this insight was that one did not need to know in advance what color a star ought to be, because the spectral lines themselves provided the reference points, and by measuring how far the lines had shifted from their laboratory positions, one could calculate the velocity of the star along the line of sight. This particular component of a star's motion, the part that is directed either toward or away from the observer, came to be called the radial velocity, to distinguish it from the transverse motion across the sky that astronomers could measure by watching stars drift slowly against the background of more distant stars over many years. For 20 years after Fizeau published his analysis, the measurement of stellar radial velocities remained beyond the reach of existing technology, because the shifts involved were extraordinarily small, far smaller than the width of the spectral lines themselves, and detecting them required instruments of greater precision than any that existed at the time. But in 1868, at the Royal Observatory in Greenwich, the English astronomer William Herschel succeeded in making the first measurement of a stellar radial velocity, turning his spectroscope towards Sirius, the brightest star in the night sky, and carefully comparing the positions of its spectral lines to the positions of lines produced by glowing hydrogen in his laboratory. Huggins was already well known for his pioneering spectroscopic studies of stars and nebulae, having demonstrated that the Orion Nebula was composed of glowing gas rather than unresolved stars, and he brought the same patient, methodical approach to this new challenge. The measurement was difficult in the extreme, requiring him to superimpose the stellar spectrum and the laboratory spectrum in his eyepiece and judge by eye whether the stellar lines were shifted slightly to one side or the other. What Huggins found was that the hydrogen lines in the spectrum of Sirius were shifted toward the blue end of the spectrum, indicating that the star was approaching the Sun, and from the amount of the shift he calculated a velocity of approach of roughly 47 kilometers per second. This was a remarkable result, the first time that anyone had measured how fast a star was moving through space, and it opened up an entirely new dimension of astronomical observation, literally adding depth to our understanding of stellar motions. Later measurements would refine this figure, and it turned out that Huggins had overestimated the velocity somewhat, the true value being closer to 8 kilometers per second in the opposite direction, meaning that Sirius is actually receding from us rather slowly, but the principle had been established and the technique had been shown to work. The errors in Huggins's early measurements were understandable given the limitations of visual observation, and they would be corrected as better instruments and photographic techniques became available in the following decades. The systematic study of stellar radial velocities began in earnest in 1888, when the German astronomer Hermann Karl Vogel established a dedicated program at the Astrophysical Observatory in Potsdam, using photography to record stellar spectra rather than relying on the eye alone. Vogel had been working with stellar spectroscopy for many years, and he understood that photographic plates offered significant advantages over visual observation, because they provided a permanent record that could be measured and remeasured at leisure, and because long exposures could accumulate more light and reveal finer details than the eye could perceive in a fleeting glance through the eyepiece. At Potsdam, Vogel developed a spectrograph specifically designed for radial velocity measurements, with careful attention to mechanical stability and temperature control, and he began a methodical survey of bright stars, measuring their spectra and calculating their motions toward or away from the Sun. The following year, in 1889, Vogel made a discovery that demonstrated the power of radial velocity measurements in an entirely unexpected way. He had been observing the star Algol, which had long been known as an eclipsing variable, meaning that its brightness dipped noticeably every few days as though something were passing in front of it and blocking part of its light. Astronomers had suspected that Algol might be a binary system, with two stars orbiting around each other, and that the dips in brightness occurred when the fainter star passed in front of the brighter one as seen from Earth. Vogel confirmed this interpretation spectroscopically by showing that the radial velocity of Algol changed in a regular, periodic fashion, shifting first toward the blue and then toward the red as the visible star swung first toward Earth and then away from Earth in its orbit around the unseen companion. This was the first spectroscopic binary system to be discovered, and it revealed that radial velocity measurements could detect stellar companions that were far too close to their primary stars to be seen as separate points of light in any telescope. The spectroscopic study of motion was not limited to stars alone, and in 1895, the American astronomer James Keeler used the technique to resolve a long-standing question about the nature of Saturn's rings. Ever since the rings had been observed through telescopes, there had been debate about whether they were solid structures, like vast circular disks of ice or rock, or whether they were composed of countless small particles, each orbiting Saturn independently like a swarm of tiny moons. The Scottish physicist James Clerk Maxwell had argued on theoretical grounds that solid rings would be unstable and would quickly break apart, and that the rings must therefore consist of separate particles, but observational confirmation of this prediction had been lacking. Keeler pointed his spectrograph at Saturn and measured the Doppler shifts at different positions across the rings, comparing the inner edge of the rings, which lies closer to Saturn, with the outer edge, which lies farther away. If the rings were solid, like a phonograph record spinning on a turntable, the outer edge would be moving faster than the inner edge, because it would have to complete a larger circle in the same amount of time. But Keeler found exactly the opposite, that the inner edge of the rings was moving faster than the outer edge, just as the inner planets of our solar system orbit the Sun faster than the outer planets, and this differential rotation proved conclusively that the rings were not solid but were indeed composed of myriad independent particles, each following its own orbit around Saturn in accordance with the laws of gravity. As the 19th century gave way to the 20th, astronomers began to turn their spectroscopes toward objects far more distant than individual stars, and in doing so they made discoveries that would eventually transform our understanding of the scale and structure of the universe. At the Lowell Observatory in Flagstaff, Arizona, a patient and meticulous observer named Vesto Melvin Slipher undertook the challenging task of measuring the radial velocities of the spiral nebulae, those faint, fuzzy patches of light that had puzzled astronomers for generations and whose true nature remained the subject of fierce debate. Some astronomers believe that the spiral nebulae were relatively nearby clouds of gas and dust within our own Milky Way galaxy, while others suspected that they might be entire galaxies in their own right, vast collections of billions of stars lying at almost unimaginable distances beyond our own stellar system. The spectra of spiral nebulae were exceedingly faint, far fainter than the spectra of individual stars, and obtaining a useful photograph of a nebula spectrum required exposure times of many hours spread over multiple nights. Slipher persevered with this difficult work, and in 1912 he succeeded in measuring the radial velocity of the Andromeda Nebula, the largest and brightest of the spiral nebulae in the northern sky. The result was startling, even to Slipher himself, because the Doppler shift indicated that Andromeda was approaching the Sun at a velocity of roughly 300 kilometers per second, a speed far greater than any stellar velocity that had ever been measured. Over the following years, Slipher continued his observations and measured the velocities of more than 40 spiral nebulae, presenting his accumulating results at scientific meetings and publishing them in the observatory's bulletin. What emerged from this patient work was a remarkable pattern, for while a few of the spiral nebulae, like Andromeda, showed blue shifts indicating approach, the great majority showed red shifts, and some of these redshifts were extraordinarily large, implying velocities of recession that reached into the hundreds and even thousands of kilometers per second. The spiral nebulae, whatever they might be, were moving through space at speeds that dwarfed the motions of ordinary stars. Slipher's measurements were quiet, careful contributions to the scientific literature, and their full significance would not become apparent until other astronomers combined them with independent estimates of the distances to the spiral nebulae, work that would unfold over the following decade and lead eventually to the recognition that the universe itself was expanding, carrying the distant galaxies away from one another like raisins in a rising loaf of bread. But that realization lay in the future, and for now, the Doppler effect had simply demonstrated its power as a tool for measuring cosmic velocities, revealing that the stars and nebulae were not fixed and motionless in their places but were streaming through space in all directions, approaching and receding, orbiting and spinning, and that all of this motion was written in the shifting lines of their spectra, waiting to be read by anyone with the patience and skill to decode it. When we look up at the night sky and see what appears to be a single point of light, we are often seeing something far more complex than our eyes can discern, for many of those gentle pinpricks of brightness are in fact two stars, or sometimes even more, bound together by gravity and circling one another in an endless celestial dance that has continued for billions of years. For most of human history, we had no way of knowing this about the more distant pairs, since even the finest telescopes could not separate stars that orbited too closely together, their light merging into what seemed to be a single source. But in the final decades of the 19th century, astronomers discovered that the spectroscope could reveal these hidden companions through a subtle effect that required patience and careful observation to detect, and this discovery opened an entirely new chapter in our understanding of how stars behave and, perhaps most importantly, how much they weigh. The story of spectroscopic binaries, as these hidden double stars came to be called, begins in the year 1889 at the Harvard College Observatory, where Edward Charles Pickering had been directing an ambitious program to classify and catalog the spectra of as many stars as possible. Pickering was a methodical and patient man who understood that great discoveries often emerge not from sudden insight but from the steady accumulation of careful observations over many years, and he had assembled a remarkable team of assistants, many of them women who would go on to make fundamental contributions to astronomy in their own right. It was during this systematic work that Pickering noticed something peculiar about the spectrum of Mizar, the middle star in the handle of the Big Dipper, a star that generations of observers had used to test the sharpness of their eyesight since it has a faint companion called Alca visible nearby to those with good vision. What Pickering observed was that certain dark absorption lines in Mizar's spectrum appeared to split into two distinct lines at regular intervals, then merge back together, then split apart again in a rhythm that repeated over a period of roughly 20 days. This was not an instrumental effect or an error in observation, for the doubling appeared and disappeared with clockwork regularity, and after careful consideration Pickering realized that he was seeing the combined light of two stars orbiting so closely together that no telescope could ever hope to separate them visually. When the two stars moved in their orbits such that one was approaching Earth while the other was receding, the Doppler effect shifted their spectral lines in opposite directions, the approaching star's lines moving slightly toward the blue end of the spectrum, while the receding star's lines shifted toward the red, and this caused the single line to appear as two. When the stars moved across our line of sight, neither approaching nor receding significantly, their lines merged back together into one. Pickering published this discovery in 1889, and Mizar thus became the first spectroscopic binary star ever identified, though it would soon have company. At almost exactly the same time, quite independently and working at the Potsdam Observatory in Germany, Hermann Karlvogel was making a similar discovery about an entirely different star. Vogel had been studying Algol, the famous variable star in the constellation Perseus that had puzzled observers for centuries with its regular dimming every 2.5 days or so. By 1889, it was already suspected that Algol's variations were caused by a dimmer companion star passing in front of the brighter one, blocking some of its light from our view in what we now call an eclipsing binary system. But Vogel went further by carefully measuring the Doppler shifts in Algol's spectral lines over the course of its orbital period, and he was able to trace out what astronomers call a spectroscopic orbit, showing how the visible star's velocity toward and away from Earth changed as it swung around its invisible companion. This was a beautiful confirmation that Algol was indeed a binary system, and Vogel's work demonstrated that the spectroscope could not only detect binary stars but could also tell us about the shapes and sizes of their orbits. Back at Harvard, the investigation of Mizar continued, and it was a young astronomer named Antonia Mori who made the next surprising discovery about this already remarkable star system. Mori had joined the Harvard Observatory staff and was engaged in the detailed classification of stellar spectra, work that required exceptional care and an eye for subtle differences that others might overlook. In 1889, the same year as Pickering's discovery, Mori turned her attention to the spectra of other stars in the Mizar system, including the nearby star Alka, which had long been considered merely a chance alignment rather than a true companion to Mizar. What Mori found was that Alka itself showed evidence of being a spectroscopic binary, its lines also splitting and merging over time, which meant that what appeared to be two stars to the naked eye was in fact at least four stars bound together in a complex gravitational arrangement. The Mizar system has since been found to be even more complex than Mori realized, but her early recognition of Alka's binary nature was an important step in understanding just how common multiple star systems truly are in our galaxy. The importance of spectroscopic binaries extended far beyond merely counting how many stars existed in various systems, for these hidden double stars provided astronomers with something they had long sought and had no other way to obtain, which was a method for determining the masses of stars. The mass of a star, meaning the total amount of matter it contains, is perhaps the single most important property governing how that star will live and die, determining how hot it will burn, how long it will shine, and what sort of remnant it will leave behind when its fuel is exhausted. Yet mass is extraordinarily difficult to measure directly for objects so distant that we can never hope to place them on a scale, and for isolated single stars we must rely on indirect methods that carry considerable uncertainty. Binary stars offer a solution to this problem because they obey the same laws of orbital mechanics that Johannes Kepler worked out for the planets 3 centuries earlier, and if we can measure the size of their orbit and the period of their revolution, we can calculate the combined mass of both stars using straightforward mathematics. For spectroscopic binaries, the Doppler shifts in the spectral lines tell us how fast each star is moving in its orbit, and the time it takes for the lines to complete a full cycle of splitting and merging tells us the orbital period. From these measurements, we can work out the size of the orbit, though with one important limitation, which is that we usually cannot tell how the orbit is tilted relative to our line of sight. An orbit seen edge-on will show the full velocity of the stars, while an orbit seen face-on will show almost no Doppler shift at all, and most orbits fall somewhere in between. This means that spectroscopic binaries usually give us only a lower limit on the stellar masses, unless we have some additional information about the orbital inclination. But even with this limitation, spectroscopic binaries revolutionized our understanding of stellar masses, providing the first reliable measurements that could be compared from star to star and used to investigate how mass relates to other stellar properties like luminosity and temperature. The case of Capella illustrates how these techniques were applied to specific stars as the 19th century drew to a close. Capella is one of the brightest stars in the northern sky, a golden point of light in the constellation Auriga that has been known since antiquity, and in 1899 Hugh Frank Newell at Cambridge Observatory in England obtained spectra showing that it too was a spectroscopic binary with its lines splitting and merging over a period of about 104 days. Newell's observations revealed that Capella consists of two giant stars, both considerably larger and more luminous than our Sun, orbiting their common center of mass in paths that bring them no closer together than about the distance from the Sun to Venus. This was a star that had seemed so simple for so many centuries, just another bright point of light, and now it was revealed to be a dynamic system of two massive stars forever circling one another. As the 20th century began, astronomers increasingly recognized that understanding binary stars was essential to understanding stars in general, and new methods were developed to extract even more information from these systems. At Princeton University, a young astronomer named Henry Norris Russell began in 1912 to focus particularly on eclipsing binary stars, those special cases where the orbital plane is aligned nearly edge-on to our line of sight so that the two stars periodically pass in front of one another. Russell realized that by carefully analyzing the way the light from such a system varies as the eclipses occur, one could determine not only the relative sizes of the two stars but also how bright different parts of their surfaces are, a phenomenon called limb darkening where the edges of a star appear slightly fainter than the center. His methods for analyzing eclipsing binaries, developed over many years at Princeton, became standard tools that astronomers would use throughout the 20th century, and they provided some of the most precise measurements of stellar sizes and masses available before the space age. The systematic study of stellar motions through spectroscopy reached an impressive scale at Lick Observatory in California, where William Wallace Campbell directed a radial velocity program that would eventually catalog the motions of over 1,000 stars. Campbell had come to Lick in 1891 and quickly recognized that measuring stellar velocities through Doppler shifts was work that could be done systematically and comprehensively if one had the patience and the proper instruments. Over the following decades, he and his colleagues accumulated velocity measurements for star after star, building up a picture of how the stellar population in our corner of the galaxy moves and flows. By 1928, the Lick program had published velocities for more than 1,000 stars, a monumental achievement that required tens of thousands of individual spectroscopic observations, each one carefully measured and reduced to extract the tiny Doppler shifts that revealed whether a star was approaching us or receding and at what speed. Many of these stars turned out to be spectroscopic binaries, their velocities varying systematically over time as they orbited unseen companions. One of the most profound conclusions to emerge from these decades of spectroscopic binary research was the recognition that solitary stars like our Sun are actually rather unusual in the cosmos. As more and more stars were examined carefully, a significant fraction turned out to be binaries or members of even larger multiple systems, and astronomers eventually concluded that most stars exist in pairs or groups rather than in isolation. This realization changed how we think about star formation, for it suggested that the collapse of a gas cloud into a new star very often produces two or more stars together rather than just one, and that gravitational interactions during the birth process tend to leave stars bound to companions. Our own Sun, drifting alone through space with only its family of planets for company, may be something of an exception rather than the rule, a solitary traveler in a galaxy where most stars have stellar companions. The techniques developed in this era, from Pickering's first recognition of line doubling in Mizar through Campbell's comprehensive velocity surveys, establish methods that astronomers continue to use today, refined by better instruments and more precise measurements but fundamentally unchanged in their basic principles. When we see the spectral lines of a star shift back and forth in wavelength over time, we know that the star is not alone, that somewhere in the darkness near it there orbits another star, pulling it first one way and then another in an endless gravitational conversation. And from the rhythm of that conversation, from the periods and amplitudes of the Doppler shifts, we can learn the most fundamental things about both stars, their masses, the sizes of their orbits, and something of their history. It is a gentle kind of detection, requiring nothing more than the patient collection of starlight over many nights and the careful measurement of where the dark lines fall upon the spectrum. On the evening of the 29th of August, 1864, an English amateur astronomer named William Huggins pointed his telescope toward a small, somewhat peculiar object in the constellation Draco, an object that catalogues listed simply as NGC 6543, though it would later become known by the more evocative name of the Cat's Eye Nebula. The night was reasonably clear over Tulse Hill in South London, where Huggins had established his private observatory some years earlier, and he had fitted his instrument with a spectroscope, that ingenious arrangement of prisms and lenses that could spread the light from distant objects into its constituent colors and reveal something of the physical nature of matter across unimaginable distances. What he observed that night would prove to be one of those quiet moments in the history of science when a single observation fundamentally alters the way we understand the universe around us, though of course Huggins could not have known the full implications as he sat there in the darkness, carefully noting what he saw through the eyepiece of his spectroscope. Up until this point, the nebulae had presented astronomers with a persistent and rather vexing puzzle. These fuzzy, cloud-like patches of light scattered across the night sky had been catalogued in increasing numbers since the 18th century, when Charles Messier and later William Herschel had compiled their lists of these objects partly as a service to common hunters who might otherwise mistake them for their quarry. The question that remained stubbornly unanswered was whether these nebulae were truly clouds of some luminous gas or vapor, or whether they might instead be vast collections of stars so distant and so numerous that no telescope yet built could resolve them into their individual points of light. Some astronomers favored the gaseous interpretation, while others, noting that more powerful telescopes did seem to resolve some nebulae into stars, suspected that all of them might eventually yield to improved instruments. The matter seemed impossible to settle through visual observation alone, no matter how large or finely crafted the telescope might be. Huggins had already achieved considerable success in applying the new science of spectroscopy to the stars, working closely with his neighbor William Allen Miller, a professor of chemistry at King's College London who provided much of the technical expertise in the early years. Together, they had demonstrated that the dark absorption lines in stellar spectra corresponded to the same chemical elements that could be identified in laboratories here on Earth, thereby establishing that the stars were made of the same fundamental substances as our own planet and sun. This was itself a profound discovery, suggesting a material unity to the cosmos that earlier generations could only have imagined. But the nebulae presented a different sort of challenge, and when Huggins turned his spectroscope toward the Cat's Eye Nebula on that August evening, he was hoping to gather evidence that might help resolve the long-standing debate about their nature. What he saw through the eyepiece was unexpected and immediately striking. Instead of the continuous rainbow band of color crossed by dark absorption lines that characterize the spectra of stars, the Cat's Eye Nebula displayed something entirely different. The spectrum consisted of just a few bright lines, isolated bands of color appearing against an otherwise dark background. This was an emission spectrum, the kind of pattern produced by a hot, diffuse gas rather than a dense, glowing solid or liquid surface. Huggins later described the moment with characteristic understatement, noting simply that the riddle of the nebulae was solved, and that the light from this particular object, and presumably from others like it, came not from an aggregation of distant stars but from a luminous gas. The nebula was genuinely a cloud, a vast expanse of incandescent matter spread across an almost inconceivable volume of space. Examining the bright emission lines more closely, Huggins was able to identify some of them with elements already known from laboratory spectroscopy. One prominent line corresponded to hydrogen, that simplest and lightest of all elements, which apparently constituted a significant portion of the nebula gas. This finding was not entirely surprising, as hydrogen had already been identified in the spectra of the Sun and various stars. But there was another line, a bright green emission at a wavelength that Huggins measured at approximately 507 nanometers, which did not correspond to any element known to terrestrial chemistry. Here was a genuine mystery, a spectral signature that seemed to belong to no substance that had ever been isolated or studied in any laboratory on Earth. Huggins and other spectroscopists of the era quite reasonably supposed that this green line must belong to an element not yet discovered, one that might exist only in the peculiar conditions found within these cosmic clouds. They gave this hypothetical element the provisional name nebulium, following the tradition that had seen helium named after the Sun when its spectral lines were first detected in solar observations before the element was identified on Earth. The nebulium lines became something of a standing puzzle in astrophysics, one that would persist for more than 60 years before its ultimate resolution, and we shall return to that resolution presently. For now, it is enough to note that Huggins had demonstrated beyond reasonable doubt that at least some of the nebulae were genuinely gaseous, and that this discovery opened an entirely new avenue for investigating the composition and physical state of matter in the depths of space. In the years that followed, Huggins continued his spectroscopic investigations with increasing skill and sophistication, and his work took on a new dimension with the involvement of Margaret Lindsay Murray, whom he married in 1875. Margaret Huggins was not merely a supportive spouse who happened to assist with occasional observations, as the conventions of Victorian biography might suggest. She was a genuine collaborator and co-investigator, possessed of considerable scientific ability in her own right, and the work that emerged from the Tulse Hill Observatory over the following decades reflected her contributions as fully as his. She had developed an interest in astronomy and spectroscopy before their marriage, having taught herself the fundamentals of the science and constructed some of her own equipment, and she brought to their partnership both technical competence and a meticulous attention to the details of measurement and recording. Together, William and Margaret Huggins pursued an extensive program of stellar and nebula spectroscopy, refining their techniques and accumulating a substantial body of observations over nearly 25 years of joint work. The culmination of their collaboration came with the publication in 1899 of their Atlas of Representative Stellar Spectra, a comprehensive volume that presented detailed spectroscopic data along with extensive discussion of methods and interpretations. The atlas was explicitly co-authored, with Margaret Huggins's name appearing alongside her husband's on the title page, an acknowledgement of her role that was by no means universal in scientific publications of the period. The work represented not only a summary of their observational achievements but also a careful exposition of spectroscopic technique that would serve as a reference for astronomers for years to come. The collaboration between William and Margaret Huggins illustrates a broader pattern in the history of science, where the contributions of women working alongside male relatives or colleagues were often minimized or overlooked in contemporary accounts, and only later scholarship has restored a fuller picture of their involvement. Margaret Huggins's careful work on the photographic and instrumental aspects of their spectroscopy, her patience with the long exposures and precise measurements required, and her intellectual engagement with the interpretation of their results all contributed substantially to the achievements credited to the Tulse Hill Observatory. The gentle persistence required for such work, night after night, adjusting instruments and recording observations with painstaking care, deserves recognition as much as any single dramatic discovery. William Huggins also turned his attention to transient celestial phenomena when the opportunity arose. In May of 1866, a star in the constellation Corona Borealis suddenly brightened from obscurity to naked eye visibility, an event classified as a nova, from the Latin word for new. This object, designated T Coronae Borealis, offered Huggins a chance to examine the spectrum of a star in the throes of some violent outburst, and his observations revealed bright emission lines indicative of rapidly expanding gas, quite different from the absorption spectra of ordinary stable stars. Such observations provided early clues to the physical processes occurring during these stellar eruptions, though a full understanding of novae would require many more decades of theoretical and observational work. Meanwhile, the puzzle of the mysterious nebulium lines remained unsolved, passing from one generation of spectroscopists to the next. Various hypotheses were proposed, including the possibility that nebulium might be an extremely light element, perhaps even lighter than hydrogen, or that it might represent some form of matter existing only under the extraordinarily rarefied conditions of interstellar space. The lines appeared consistently in the spectra of many gaseous nebulae, always at the same wavelengths, which suggested a genuine element rather than some instrumental artifact or measurement error. Yet no laboratory experiment could reproduce these lines, and Nebulium remained a theoretical placeholder rather than a confirmed member of the periodic table. The solution came at last in 1927 through the work of an American physicist and astronomer named Ira Sprague Bowen, working at the California Institute of Technology. Bowen approached the problem not by searching for a new element, but by reconsidering the behavior of elements already known under conditions that could not be replicated in any terrestrial laboratory. He demonstrated that the green nebulium lines, along with certain other previously unexplained nebular emissions, were in fact produced by oxygen and nitrogen, two of the most common elements in the universe. The key to understanding this lay in what physicists call forbidden transitions, quantum mechanical processes that have an exceedingly low probability of occurring under normal circumstances. In a laboratory setting, atoms of oxygen and nitrogen are constantly colliding with one another, and these collisions cause excited atoms to release their energy through ordinary permitted transitions long before a forbidden transition can occur. But in the near-perfect vacuum of a gaseous nebula, where atoms may drift for hours or even days without encountering another particle, there is ample time for these rare forbidden transitions to take place. The green line that Huygens had observed in 1864 was produced by doubly ionized oxygen atoms that had lost two of their electrons, undergoing a transition that simply could not be observed on Earth because the necessary conditions of extreme low density could not be maintained for long enough. Nebulium, it turned out, had been oxygen all along, merely behaving in ways that required the vast emptiness of interstellar space to manifest. While Huygens and others probed the composition of bright nebulae through spectroscopy, a different kind of nebula was being revealed through the patient work of astronomical photography. Edward Emerson Barnard, an American astronomer who rose from poverty to become one of the most skilled observers of his generation, carried out extensive photographic surveys of the Milky Way from his post at Lick Observatory in California. Among his many discoveries were the curious dark patches and lanes that seemed to obscure portions of the star fields, regions where stars appeared to be absent or greatly reduced in number. Barnard recognized that these were not true voids but rather clouds of dark, non-luminous material that blocked the light from more distant stars behind them. These dark nebulae represented yet another component of the interstellar medium, vast accumulations of dust and gas that emitted no light of their own and could be detected only by their obscuring effect. The nature of the spiral nebulae, those graceful pinwheel-shaped objects that showed neither emission spectra nor simple stellar character, remained deeply uncertain into the 20th century. Some astronomers believe these spirals to be relatively nearby features within our own Milky Way galaxy, perhaps solar systems in the process of formation or clouds of gas being shaped by rotation. Others argued that they might be independent systems of stars, what the philosopher Immanuel Kant had long ago called island universes, vast aggregations of suns comparable in scale to the Milky Way itself but lying at immense distances beyond it. This debate came to a head in 1920, when two distinguished American astronomers, Harlow Shapley and Heber Curtis, presented opposing views in what became known as the Great Debate, held at the Smithsonian Institution in Washington. Shapley argued for a large Milky Way with the spirals as minor features within it or nearby, while Curtis maintained that the spirals were external galaxies at great distances. The question would not be definitively resolved for several more years, but the debate itself highlighted how much remained unknown about the fundamental scale and structure of the cosmos, even as spectroscopy continued to reveal the chemical composition of celestial objects with increasing precision. And so the study of nebulae, from the bright emission clouds to the dark obscuring regions to the enigmatic spirals, gradually expanded the horizons of human understanding, revealing a universe far richer and more complex than earlier generations had imagined. The quiet observations made from small observatory domes, the careful measurements of spectral lines, the patient accumulation of photographic plates, all contributed to a picture of cosmic structure that was still unfolding as the 20th century began. Each answered question seemed to raise new ones, and each new technique opened fresh avenues of investigation, yet the fundamental approach remained the same, the careful analysis of light, that messenger from the depths of space, revealing its secrets to those with the patience and skill to read them. There is something quite remarkable, in a quiet sort of way, about how the deepest mysteries of the universe sometimes reveal themselves not in grand observatories or well-funded laboratories, but in modest schoolrooms and at the desks of patient teachers who have lived long enough to cultivate both wisdom and the particular kind of stubbornness that allows a person to spend years contemplating a puzzle that others might dismiss as merely curious. And so we come to Johann Jakob Balmer, a Swiss mathematician who spent most of his working life teaching at a girls' school in the pleasant city of Basel, where the Rhine curves gently between France and Germany, and where the days passed in the agreeable rhythm of lessons and grading and the occasional afternoon walk along the river. Balmer was 60 years old in 1885, an age when many scholars have long since made whatever contributions they might make to human knowledge, and yet it was precisely at this late stage of his career that he turned his attention to a problem that had puzzled physicists for decades, namely the curious pattern of colored lines that appeared when hydrogen gas was made to glow and its light was spread out by a prism into a spectrum. These lines had been observed and measured with considerable precision by the Swedish physicist Anders Ångström, whose name would later be given to the unit of measurement commonly used for the wavelengths of light, and Balmer, being a mathematician rather than a physicist, approached the problem not by asking what physical mechanism might produce such lines but simply by asking whether the measured wavelengths might follow some mathematical pattern, some formula that could predict where each line would fall. It was the kind of question that a mathematician might naturally ask, and Balmer, with the patience of a man who had spent decades teaching young people to appreciate the elegance of numerical relationships, set about trying one formula after another until at last he found one that worked. The formula he discovered was remarkably simple, expressing the wavelength of each visible line in the hydrogen spectrum in terms of whole numbers, specifically the squares of whole numbers, and when he tested his formula against Ångström's careful measurements, the agreement was extraordinarily close, to within a fraction of a percent, which suggested that he had found something genuine rather than merely coincidental. What Balmer had discovered, though he did not fully understand its significance at the time, was that the visible spectral lines of hydrogen could all be described by a single formula involving the number 4 and a sequence of other integers beginning with 3, 4, 5, and continuing onward, and he speculated, quite correctly as it turned out, that there might be other series of lines in the hydrogen spectrum corresponding to other choices of that fundamental number, series that might lie in the invisible ultraviolet or infrared regions of the spectrum where the human eye could not perceive them. This was a prediction that would be verified in the years that followed, as experimenters with appropriate instruments found precisely the lines that Balmer's formula had implied should exist, lines in the ultraviolet discovered by Theodor Lyman and lines in the infrared found by Friedrich Paschen and later by others, each series fitting neatly into the pattern that the elderly schoolteacher from Basel had discerned. 3 years after Balmer's discovery, a Swedish physicist named Johannes Rydberg undertook to generalize this curious formula, seeking a single mathematical expression that could describe not only Balmer's series but all the other series as well, and indeed not only the spectrum of hydrogen but potentially the spectra of other elements too. Rydberg was a methodical man, fond of patterns and regularities, and he spent years compiling spectral data and searching for the underlying order, driven by an almost aesthetic conviction that nature must be fundamentally simple and mathematically elegant. In 1888, he published a formula that expressed the frequencies of spectral lines in terms of the difference between two quantities, each quantity being the same constant divided by the square of a whole number, and this constant, which appeared in the formula as a sort of fundamental unit, came to be called the Rydberg constant in his honor. The Rydberg constant proved to be one of the fundamental constants of nature, as basic in its way as the speed of light or the charge of the electron, though its true meaning would not become clear until the quantum theory had been developed to explain why such a constant should exist at all. For the moment, however, these formulas remained purely empirical, which is to say that they described the patterns in the data without explaining why those patterns existed, much as Kepler's laws had once described the motions of the planets without explaining what force kept them in their orbits. The explanation would require a revolution in physics, a revolution that began on a cold December evening in the year 1900, when a German physicist named Max Planck stood before the German Physical Society in Berlin and presented a theoretical derivation that would eventually overturn the classical understanding of energy and matter. The date was the 14th of December, and Planck, a conservative and rather formal man who had devoted much of his career to the study of thermodynamics, was attempting to explain the spectrum of radiation emitted by a perfect absorber of light, what physicists call a blackbody, a problem that had resisted all attempts at solution using the established principles of physics. The difficulty was this: according to classical theory, a heated object should radiate energy at all wavelengths, and the amount of energy radiated at short wavelengths should increase without limit, a prediction that was clearly absurd since it implied that even a lukewarm object should be emitting deadly amounts of ultraviolet and X-ray radiation, which it manifestly was not. This absurd prediction had come to be called the ultraviolet catastrophe, and Planck, after struggling with the problem for months, found that he could avoid it only by making an assumption that seemed, at the time, to be little more than a mathematical trick, namely that energy could not be emitted or absorbed in arbitrary amounts but only in discrete packets, which he called quanta, with the size of each quantum proportional to the frequency of the radiation. The constant of proportionality in this relationship is now called Planck's constant, and it is one of the fundamental constants of nature, a number so small that its effects are imperceptible in everyday life but so profound in its implications that it would reshape our entire understanding of the physical world. Planck himself was not entirely comfortable with what he had done, regarding the quantum hypothesis as a provisional assumption rather than a fundamental truth, and it fell to a young patent clerk in Bern, Switzerland, to take the next decisive step. In 1905, a year that would later be called his miracle year, Albert Einstein published a paper on what is called the photoelectric effect, the phenomenon by which light striking a metal surface can eject electrons from that surface. The puzzling feature of this effect was that it depended not on the intensity of the light but on its frequency. Dim blue light could eject electrons while bright red light could not, no matter how intense the red light might be. Einstein explained this by proposing that light itself consists of discrete packets of energy, which we now call photons, each photon carrying an amount of energy proportional to the frequency of the light, and an electron could be ejected only if a single photon carried enough energy to overcome the forces binding the electron to the metal. This was a far more radical proposal than Planck's original hypothesis, for it suggested that the quantum was not merely a feature of how energy was emitted and absorbed but a fundamental property of light itself, and although the full implications of this idea would take decades to work out, it marked the beginning of quantum theory as a new branch of physics. The connection between these quantum ideas and the spectral lines that Balmer and Rydberg had studied so carefully was made in 1913 by a young Danish physicist named Niels Bohr, who had come to England to work first with J.J. Thomson and then with Ernest Rutherford, whose laboratory in Manchester was at the forefront of research into the structure of the atom. Rutherford had recently discovered that atoms consist of a tiny, dense, positively charged nucleus surrounded by electrons, but this model posed a serious problem. According to classical physics, an electron orbiting a nucleus should continuously radiate energy, spiraling inward until it crashed into the nucleus, a process that should take only a tiny fraction of a second. Atoms, in other words, should not be stable, and yet they manifestly were. Bohr solved this problem by proposing that electrons could occupy only certain special orbits around the nucleus, orbits in which the angular momentum of the electron was a whole number multiple of Planck's constant divided by 2 pi, and that electrons in these allowed orbits did not radiate energy. When an electron jumped from one allowed orbit to another, it would emit or absorb a photon whose energy was exactly equal to the difference in energy between the two orbits, and since only certain orbits were allowed, only certain energies of photons could be emitted, producing the discrete spectral lines that had been observed. When Bohr applied this model to the hydrogen atom, he found that it predicted exactly the spectral lines that Balmer had described, with the Rydberg constant emerging naturally from the calculation in terms of the fundamental constants of nature, the mass and charge of the electron and Planck's constant. This was a remarkable achievement, for it meant that the mysterious patterns in the hydrogen spectrum, which had seemed to be merely empirical regularities, were in fact consequences of the quantum structure of matter, and the Rydberg constant, which Rydberg himself had simply measured from the data, could now be calculated from first principles. Bohr's model was not the final word on atomic structure, for it could not fully explain the spectra of atoms with more than one electron, and it contained assumptions that seemed arbitrary and ad hoc, but it established beyond doubt that the quantum hypothesis was the key to understanding the inner workings of atoms. Einstein, meanwhile, continued to develop quantum ideas, and in 1916 he published a paper in which he analyzed the ways in which atoms could interact with radiation. He identified three processes: absorption, in which an atom absorbs a photon and jumps to a higher energy state; spontaneous emission, in which an atom in a higher energy state spontaneously drops to a lower state and emits a photon; and a third process that Einstein called stimulated emission, in which a photon passing by an excited atom can cause that atom to emit an identical photon with the same frequency, direction, and phase as the original. This third process would eventually become the basis of laser technology, though that development lay far in the future, and for the moment it was simply another piece of the quantum puzzle that physicists were gradually assembling. Also in 1916, the German physicist Arnold Sommerfeld published refinements to Bohr's model that addressed some of its limitations. Where Bohr had assumed that electrons moved only in circular orbits, Sommerfeld showed that elliptical orbits were also allowed, introducing additional quantum numbers to describe the shape and orientation of the orbits. These refinements helped explain some of the finer details of atomic spectra that Bohr's original model could not account for, and they pointed the way toward the more complete quantum theory that would be developed in the 1920s. Before we leave this era, we should mention a phenomenon discovered in 1896 by the Dutch physicist Peter Zeeman, who observed that when a light source was placed in a strong magnetic field, its spectral lines would split into multiple components. This effect, which came to be called the Zeeman effect, was quickly explained by another Dutch physicist, Hendrik Lorentz, who showed that the splitting could be understood in terms of the effect of the magnetic field on the orbiting electrons in the atom, and for their work on this phenomenon Zeeman and Lorentz shared the Nobel Prize in Physics in 1902. The Zeeman effect would prove to be an invaluable tool for astronomers, who could use it to measure the magnetic fields of distant stars and other celestial objects by observing the splitting of their spectral lines, and it also provided important clues about the internal structure of atoms that would help guide the development of quantum theory. And so, by the second decade of the 20th century, the quantum key had been found, and the spectral lines that had seemed so mysterious to Fraunhofer and Kirchhoff and Bunsen could at last be understood as windows into the quantum structure of atoms, each line a precise signature of the energy levels within the atom and the transitions between them. The patient work of observers and the inspired insights of theorists had combined to reveal that light carries information not only about the composition of matter but about the deepest laws that govern how matter is put together, and this understanding would transform spectroscopy from a tool of chemical analysis into a probe of fundamental physics, with implications that extended from the smallest scales of atomic structure to the grandest scales of the cosmos itself. As the 19th century moved past its midpoint and began its long, gentle slope toward a new era, the study of the heavens was undergoing a quiet but profound transformation, one that would see the construction of entirely new kinds of institutions dedicated not merely to measuring the positions of stars, as observatories had done for centuries, but to understanding what those distant points of light actually were, what they were made of, and how they behaved according to the same physical principles that governed matter here on Earth. This shift in purpose, from the ancient art of positional astronomy to the newer science of astrophysics, required new tools, new methods, and indeed new places of research, and so in various countries around the world, far-sighted scientists began to establish observatories with instruments and programs specifically designed to capture and analyze starlight in ways that would have seemed almost magical to earlier generations of astronomers. Among the earliest and most significant of these new institutions was the Astrophysical Observatory at Potsdam, established in 1874 in the Kingdom of Prussia, which holds the distinction of being the first observatory in the world founded with the explicit purpose of pursuing astrophysical research rather than traditional positional astronomy. The observatory was situated on the Telegraphenberg, a gentle hill near Potsdam, and its founding represented a recognition by the Prussian scientific establishment that the new techniques of spectroscopy and photometry, which allowed scientists to determine the chemical composition and physical properties of celestial bodies, deserved a dedicated institutional home with instruments and staff devoted entirely to these novel methods of investigation. The Potsdam Observatory housed spectrographs and photometers alongside more traditional telescopes, and its researchers pursued systematic programs of stellar spectroscopy, solar observation, and the measurement of stellar brightness using the precise techniques that were then being developed. This institution served as a model for observatories that would follow in other countries, demonstrating that the astrophysical approach to astronomy was sufficiently mature and promising to warrant substantial investment in buildings, instruments, and permanent scientific staff. Across the Atlantic Ocean, in the rapidly industrializing United States of America, a young and extraordinarily energetic scientist named George Ellery Hale was beginning a career that would reshape the institutional landscape of astrophysical research in ways that continue to influence the field to the present day. Hale possessed a rare combination of scientific vision, organizational talent, and the ability to persuade wealthy benefactors to fund ambitious projects, and he would go on to establish not one but several of the most important observatories of the late 19th and early 20th centuries, each one equipped with instruments larger and more powerful than those that had come before. His first major achievement in observatory building came with the establishment of the Yerkes Observatory, which opened in 1897 in Williams Bay, Wisconsin, on the shores of Lake Geneva, a location chosen for its relatively dark skies and stable atmospheric conditions. The observatory was funded by the Chicago streetcar magnate Charles Tyson Yerkes, whom Hale had convinced to provide the necessary capital, and it housed the largest refracting telescope ever built, with a lens measuring 40 inches in diameter, an instrument that represented the practical limit of what could be achieved with lens-based telescopes due to the tendency of very large glass lenses to sag and distort under their own weight. The Yerkes Observatory became a center for spectroscopic research and solar physics, attracting talented scientists and training a new generation of astrophysicists, but Hale was already looking toward even more ambitious projects. He recognized that the future of observational astronomy lay not with refracting telescopes and their glass lenses, but with reflecting telescopes that use mirrors to gather and focus light, since mirrors could be made much larger than lenses and did not suffer from the same chromatic aberration that plagued large refractors. In 1904, Hale established the Mount Wilson Observatory in the San Gabriel Mountains above Pasadena, California, a site chosen for its excellent atmospheric conditions and its elevation of nearly 1,800 meters above sea level, which placed it above much of the turbulent air and light pollution that afflicted observatories at lower altitudes. Mount Wilson would eventually house a 60-inch reflecting telescope completed in 1908 and later a 100-inch reflector completed in 1917, both of which were the largest telescopes in the world at the time of their construction, and these instruments would enable discoveries that fundamentally changed our understanding of the universe. It was at Mount Wilson, using the 60-inch reflector and specialized spectroscopic equipment, that Hale made one of his most significant personal discoveries in 1908, when he detected the presence of magnetic fields and sunspots through the observation of a phenomenon known as the Zeeman effect. This effect, named after the Dutch physicist Peter Zeeman who had discovered it in laboratory experiments in 1896, causes spectral lines to split into multiple components when the light-emitting atoms are subjected to a magnetic field, and the degree of splitting is related to the strength of that field. When Hale examined the spectra of sunspots, those dark, relatively cool regions on the solar surface that had puzzled observers since the time of Galileo, he found that certain spectral lines were indeed split in exactly the manner predicted by the Zeeman effect, demonstrating conclusively that sunspots were regions of intense magnetic activity. This discovery opened up the entirely new field of solar magnetism and provided a physical explanation for phenomena that had previously been mysterious, showing once again how the techniques of laboratory physics, when applied to celestial observations, could reveal the hidden workings of objects that had seemed forever beyond the reach of direct investigation. While Hale was building his observatories in the Midwest and California, another major American institution was pursuing its own distinguished program of spectroscopic research. The Lick Observatory, perched atop Mount Hamilton in California and opened in 1888, became one of the premier centers for stellar spectroscopy under the leadership of scientists such as James Keeler and William Wallace Campbell. Keeler, who served as director of the observatory and made important contributions to the study of planetary rings and nebulae, helped establish rigorous programs of spectroscopic observation that systematically catalogued the spectra of stars and other celestial objects. Campbell, who succeeded Keeler as director after the latter's untimely death in 1900, devoted much of his career to the measurement of stellar radial velocities using the Doppler shifts in spectral lines, building up a vast catalogue of data that revealed how stars were moving toward or away from the Earth. These radial velocity measurements, accumulated over many years of patient observation, provided crucial information about the dynamics of our galaxy and the motions of stars through space, and they represented exactly the kind of systematic, long-term observational program that the new astrophysical observatories were uniquely equipped to carry out. The theoretical foundations of astrophysics were being developed alongside these observational programs, and one of the most brilliant contributors to the mathematical and physical theory underlying stellar structure and behavior was Karl Schwarzschild, a German astronomer and physicist who worked at the University of Göttingen and later at the Potsdam Observatory. Schwarzschild possessed an extraordinary mathematical gift and applied it to a wide range of problems in astrophysics, including the theory of stellar atmospheres, the behavior of light in strong gravitational fields, and the statistical mechanics of stellar systems. His work on radiative transfer, which describes how energy in the form of light moves through the outer layers of a star, provided essential tools for interpreting stellar spectra and understanding the physical conditions in stellar atmospheres. Later, while serving in the German army during the First World War, Schwarzschild found the first exact solution to Einstein's equations of general relativity, describing the gravitational field around a spherical mass, a solution that would later become fundamental to our understanding of black holes, though Schwarzschild himself did not live to see these later developments, as he died in 1916 from a disease contracted during his military service. His theoretical contributions, made during a relatively short career, demonstrated how mathematical physics could illuminate the workings of the cosmos and laid groundwork that would support astrophysical research for generations to come. The progress of spectroscopy depended not only on theoretical advances and new observatories, but also on improvements in the instruments used to disperse light into its component wavelengths. One of the most significant of these instrumental advances came from the laboratory of Henry Augustus Rowland at Johns Hopkins University in Baltimore, where in 1882 Rowland developed a new type of diffraction grating that dramatically improved the resolution and quality of spectroscopic observations. A diffraction grating works by using many closely spaced lines or grooves to break light into its spectrum, and the more lines per unit length, the greater the resolving power of the grating, meaning its ability to distinguish between spectral lines that are very close together in wavelength. Rowland developed precision ruling engines that could produce gratings with over 14,000 lines per inch, a remarkable achievement of mechanical engineering that required extraordinary care and patience, since even the slightest irregularities in the spacing of the lines would degrade the quality of the resulting spectra. Furthermore, Rowland made his gratings on concave rather than flat surfaces, which had the advantage of focusing the spectrum without the need for additional lenses, simplifying the design of spectrographs and reducing the light losses that occurred when beams passed through multiple optical elements. Rowland's gratings were distributed to observatories and laboratories around the world, and they enabled a new generation of high-resolution spectroscopic work that revealed ever finer details in the spectra of the sun, stars, and laboratory light sources. Another technological development that transformed spectroscopy during this period was the application of photography to the recording of spectra. In the early days of spectroscopy, observers had to view spectra directly with their eyes, sketching or describing what they saw and attempting to remember the positions and relative intensities of spectral lines. This method was laborious, subjective, and limited by the capabilities of human vision and memory. The introduction of photographic plates that could be placed at the focal plane of a spectrograph changed everything, for now a spectrum could be recorded permanently as a physical object that could be measured, compared with other spectra, and preserved for future reference. Photographic emulsions were often more sensitive than the human eye, particularly to blue and violet light, and a long exposure could accumulate light over hours, revealing faint spectral features that no human eye could ever have detected directly. The photographic record also allowed for precise measurement of spectral line positions using microscopes and measuring engines, enabling the calculation of wavelengths and Doppler shifts with far greater accuracy than had previously been possible. By the end of the 19th century, observatories were accumulating vast archives of photographic spectral plates, creating permanent records of stellar spectra that could be studied and restudied as theoretical understanding advanced and as new questions arose about the nature of stars. As the 20th century began, the international community of astronomers recognized the need for coordination and standardization in their rapidly growing field. The techniques of spectral classification, which had been developed somewhat independently at different observatories, needed to be harmonized so that scientists around the world could communicate clearly about the types of stars they were studying. This desire for international cooperation led eventually to the establishment of the International Astronomical Union in 1919, an organization that brought together astronomers from many countries to coordinate research programs, standardize nomenclature and classification systems, and facilitate the exchange of information and ideas. One of the early achievements of this cooperative effort was the adoption of standardized systems for spectral classification, building on the work done at Harvard and elsewhere, so that when an astronomer in one country described a star as belonging to a particular spectral class, astronomers in every other country would understand precisely what was meant. This standardization was essential for the progress of astrophysics, as it allowed the accumulation of data from many sources into coherent catalogues and enabled the statistical studies of stellar populations that would reveal the structure and evolution of our galaxy. And so, through the patient accumulation of observations, the construction of ever more capable instruments, the development of theoretical frameworks, and the establishment of institutions dedicated to the new science of astrophysics, the study of starlight was transformed from a curiosity into a mature scientific discipline. The observatories founded during this period, from Potsdam to Yerkes to Mount Wilson to Lick, became the temples of this new science, places where dedicated researchers spent long nights gathering the light of distant stars and spreading it into spectra that could be read like messages from across the void. The work was slow, methodical, and cumulative, each observation adding a small piece to a growing mosaic of understanding, and the scientists who carried out this work did so with the knowledge that they were part of an enterprise larger than any individual, one that would continue long after they themselves had laid down their instruments and rested. In the high desert of northern Arizona, where the air hangs still and cold above the volcanic plateaus, there stood in the early years of the 20th century a modest observatory that would quietly revolutionize humanity's understanding of the universe itself. Lowell Observatory had been founded in 1894 by Percival Lowell, a wealthy Bostonian whose fascination with Mars and its supposed canals had drawn him to establish his own astronomical outpost far from the humid air and city lights of the eastern seaboard. And while Lowell himself pursued his controversial theories about Martian civilizations, a young astronomer named Vesto Melvin Slipher was undertaking far less glamorous work that would prove infinitely more consequential: the systematic measurement of the spectral characteristics of faint fuzzy patches of light known as spiral nebulae, those enigmatic pinwheels whose true nature remained deeply uncertain in those years before the First World War. Slipher had arrived at Lowell Observatory in 1901, fresh from completing his studies at Indiana University, and he possessed that particular combination of patience and technical skill that makes for excellence in observational astronomy. Percival Lowell had initially set him the task of studying the rotation of planets and other bodies through spectroscopic analysis, and in pursuing this work Slipher became extraordinarily adept at coaxing meaningful measurements from the faintest possible light sources. The spiral nebulae presented a formidable challenge even for skilled observers, as their diffuse glow spread thinly across considerable areas of sky, making the collection of sufficient light for spectroscopic analysis a matter requiring exposure times of many hours across multiple nights. But Slipher had modified the observatory spectrograph to achieve remarkable sensitivity, and in 1912 he turned his attention to the brightest of the spiral nebulae, the great swirl in Andromeda that astronomers designated Messier 31. The observations required extraordinary dedication, with Slipher guiding the telescope manually through the long winter nights to keep the nebula's light precisely focused on the spectrographer's narrow slit. His first successful spectrum of Andromeda revealed something unexpected, for when he measured the positions of the absorption lines imprinted on that feeble light, he found them shifted toward the blue end of the spectrum by a substantial amount, indicating that the nebula was approaching our solar system at a velocity of approximately 300 kilometers per second. This was a startling figure, far exceeding the velocities typically measured for stars within our galaxy, and it suggested that whatever these spiral nebulae might be, they were not ordinary components of the stellar system surrounding our Sun. Over the following years, Slipher extended his measurements to other spiral nebulae, working methodically through the catalogue of known objects and accumulating velocity determinations with painstaking care. By 1917, he had measured the Doppler shifts of 25 spiral nebulae, and by 1925 his catalogue had grown to include 45 objects, representing essentially all the spiral nebulae bright enough for his equipment to analyze. And here emerged a pattern that no one had anticipated, for while a few of these objects showed blue shifts indicating approach, the overwhelming majority displayed red shifts that spoke of recession, movement away from our solar system at velocities ranging from several hundred to nearly 2,000 kilometers per second. The universe revealed by Slipher's spectrograph was one of pervasive outward motion, a cosmos in which the spiral nebulae were fleeing from us at speeds that seemed almost incomprehensible by the standards of ordinary astronomical experience. Slipher presented these findings at scientific meetings and published them in the astronomical literature, and his work attracted considerable attention, though its full significance remained obscured by the fundamental uncertainty surrounding the nature of the spiral nebulae themselves. Were these objects relatively small structures within our own Milky Way, island universes of gas and stars perhaps, or were they truly separate stellar systems comparable to our own galaxy but lying at immense distances in the depths of extragalactic space? This question, which had occupied astronomers since the 18th century musings of Immanuel Kant, could not be resolved by spectroscopy alone, for the velocity measurements told nothing about distance, and without distance one could not determine whether these receding nebulae were modest nearby objects or enormous distant ones. The resolution of this uncertainty came from the slopes of Mount Wilson in Southern California, where the Carnegie Institution had constructed what was then the largest telescope in the world, a reflecting instrument with a primary mirror 100 inches in diameter. This great eye collected light with unprecedented efficiency, and in the hands of a skilled observer it could reveal details in the spiral nebulae that no previous instrument had been able to discern. Edwin Hubble had arrived at Mount Wilson in 1919, following service in the First World War, and he brought to his work an intensity of purpose matched by considerable observational skill, though his personality, which tended towards self-promotion and occasional appropriation of others' contributions, would later complicate assessments of his legacy. Throughout the early 1920s, Hubble devoted himself to photographing the brightest spiral nebulae with the 100-inch telescope, searching for individual stars that might be resolved within their luminous swirls. In October of 1923, while examining a photographic plate of the Andromeda Nebula, he identified what he initially believed to be a nova, a stellar explosion of the type occasionally observed in our own galaxy. But as he compared the brightness of this object across multiple plates taken on different nights, he recognized that it was not a nova at all, but rather a Cepheid variable, one of those pulsating stars whose period of brightness variation bears a precise mathematical relationship to their intrinsic luminosity. Hubble crossed out the letter N he had written on the plate and replaced it with the letters VAR, for variable, and in that simple notation lay the key to measuring the distance to Andromeda. The period luminosity relationship for Cepheid variables had been established by Henrietta Swan Leavitt at Harvard College Observatory, working with stars in the Magellanic Clouds, and her discovery had provided astronomers with what they called a standard candle, a class of object whose true brightness could be determined from observable characteristics alone. By measuring the period of the Cepheid variable in Andromeda, Hubble could determine its intrinsic luminosity, and by comparing this to its apparent brightness as seen from Earth, he could calculate the distance to the nebula. The result was extraordinary, for even after accounting for all known sources of error, the Andromeda Nebula lay at a distance of approximately 1 million light-years, placing it far beyond the boundaries of our own Milky Way galaxy and establishing beyond reasonable doubt that it was itself an independent stellar system of comparable scale. Hubble announced these findings in 1924, and his demonstration of the extragalactic nature of the spiral nebulae transformed them from mysterious patches of light into what we now call galaxies, vast congregations of stars each representing a universe unto itself. And with this transformation came a new significance for Slipher's velocity measurements, for if the spiral nebulae were galaxies distributed through an immense cosmos, then their systematic recession implied something profound about the nature of space itself. The story now requires us to step back briefly to 1917, when Albert Einstein had applied his newly completed general theory of relativity to the cosmos as a whole, attempting to describe the universe in terms of curved spacetime shaped by the matter it contained. Einstein's equations, when applied to a universe uniformly filled with matter, did not yield a static solution, and this troubled him deeply, for the prevailing assumption of the time held that the universe was unchanging and eternal, neither expanding nor contracting but existing in a state of cosmic equilibrium. To achieve a static solution, Einstein introduced an additional term into his equations, a quantity he called the cosmological constant, which provided a repulsive force to exactly balance the attractive force of gravity and hold the universe in equilibrium. This modification was purely ad hoc, introduced solely to preserve the assumption of a static cosmos, and Einstein would later describe it as the greatest mistake of his career. In 1927, a Belgian priest and physicist named Georges Lemaitre approached the cosmological problem from a different perspective, accepting the expanding solutions that Einstein had rejected and developing a theoretical model of a universe that grew larger with time. Lemaitre derived a remarkable relationship between the distance to a galaxy and the velocity at which it would appear to recede, a consequence of the expansion of space itself rather than ordinary motion through space. He published his findings in the Annales de la Société Scientifique de Bruxelles, a Belgian journal with limited international circulation, and his theoretical prediction went largely unnoticed by the astronomical community, buried in an obscure publication written in French. Meanwhile, at Mount Wilson, Hubble had begun collaborating with Milton Humason on a systematic program to extend the velocity and distance measurements to more distant galaxies. Humason's presence at the Great Observatory represented one of astronomy's most remarkable stories of personal advancement, for he had begun his career as a mule driver hauling construction materials up the mountain during the building of the telescope, and his intelligence and dedication had led to successive promotions until he became one of the most skilled observers in the world, despite never having completed high school. His ability to guide the telescope through long exposures and extract spectra from the faintest possible sources would prove essential to the work that followed. In 1929, Hubble published a paper that combined his distance estimates for nearby galaxies, determined primarily through Cepheid variables and other indicators, with velocity measurements drawn largely from Slipher's earlier work and supplemented by Humason's new observations of more distant objects. Plotting velocity against distance, Hubble found a roughly linear relationship, with more distant galaxies receding at proportionally greater velocities. The constant of proportionality, which came to be called the Hubble constant, he estimated at approximately 500 kilometers per second per megaparsec, meaning that for every million parsecs of distance, a galaxy would exhibit an additional 500 kilometers per second of recessional velocity. This value, we now know, was substantially in error, too high by a factor of roughly 7, owing to systematic underestimates of galactic distances that would not be corrected for several decades. The modern value of the Hubble constant lies in the vicinity of 70 kilometers per second per megaparsec, and this correction dramatically increases the estimated age and size of the observable universe. But the fundamental insight contained in Hubble's 1929 paper was correct, that the universe is expanding, that the fabric of space itself is stretching and carrying the galaxies apart from one another in a process that has been ongoing for billions of years. Lemaitre's theoretical prediction was eventually recognized, particularly after his work was translated into English in 1931, and the expansion of the universe came to be understood as a natural consequence of general relativity rather than an anomaly requiring explanation. The cosmological constant that Einstein had introduced to prevent expansion was revealed as unnecessary, an epicycle of 20th century cosmology that served only to preserve a prejudice that the universe itself did not share. Lemaitre went further in his theoretical speculations, proposing that if the universe was expanding, then tracing this expansion backward in time would lead to a state of extreme compression, a prime-val atom as he called it, from which all matter and energy had emerged. This idea would eventually develop, through the contributions of many physicists and astronomers, into what we now call the Big Bang Theory, the modern framework for understanding the origin and evolution of the cosmos. By 1930, the transformation was essentially complete. Spectroscopy, which had begun with Fraunhofer's dark lines and Kirchhoff's kitchen salt, had grown into a tool capable of revealing the fundamental nature of the universe itself. The cosmos was no longer a matter for philosophical speculation alone, but had become amenable to empirical investigation, its structure and history written in the wavelengths of light that reached our telescopes across the immensity of intergalactic space. The redshifts measured by Slipher in his cold Arizona nights, the distances estimated by Hubble from the pulsations of Cepheid variables, the theoretical insights of Einstein and Lemaitre working with pencil and paper in their studies, all of these had converged to reveal a universe vaster, more dynamic, and more strange than anyone had imagined. And spectroscopy remained at the heart of this cosmological revolution, for it was through the careful measurement of wavelength shifts that astronomers could determine the velocities of distant objects, and it was through the analysis of spectral features that they could identify the standard candles needed to estimate distances. The rainbow had become a ruler for measuring the universe, and the dark lines that Fraunhofer had first observed in sunlight more than a century earlier had grown into a language through which the cosmos told its own story, one of expansion and evolution, of galaxies receding into the depths of space, of a universe that had a beginning and continues to change with the passing of cosmic time.